Professor Violi is a professor of mechanical engineering, chemical engineering, and biophysics at the University of Michigan. And just from that, you can see she has a very broad range of expertise. She got her PhD at the University of Naples, and then was a postdoc at the University of Utah, actually working in fire science and numerical simulations to study fires. And then she became a professor. Her first faculty position was in University of Michigan, where she developed her career there. And she leads a quite diverse group. Many of us in combustion community know her for being an expert in fuels kinetics modeling, fuel surrogate, but also understanding interactions of particulate matter with the health effects on human beings and other areas of nanoscience. In addition, she has made herself well known for works in quantum chemistry and molecular dynamics. So I'm sure you will all believe me when I say she has a very broad range of expertise, and she's going to be able to share a lot of information with us. She's held many important positions, including having the NSF Career Award from the U.S. National Science Foundation. So please welcome Angela. She'll be giving the lectures this afternoon as well as a workshop tomorrow afternoon.
Okay. Thank you. Okay, so welcome to this afternoon section. Can you hear me well? Okay, good. So my job is to entertain you for this last section of the summer school, so bear with me. I understand this afternoon. I understand that you might be tired. It's towards the end of the week for everybody. But I heard that, first of all, there are cameras. So if you fall asleep, they will tell me. There is some guy in the back, he just told me that. And I think Mani just promised something special for tomorrow. Did you? For everybody or not? That's the plan, right? Exactly. He just said yes. He didn't know anything, but he will do something special. So bear with me. And I think differently from what you heard so far, my intent for this class, for this lecture, is to give you some perspective. So I'm going to report on what is available right now in the community on those topics that Mani was mentioning. But also, I think the goal of a summer school is for you to, to broaden your interest. And so get maybe involved in something that is a little bit out of the box for you. And so, maybe explore different avenues for your future also. So, before so I don't have prizes for you guys, but are you supposed to give those away right now? Later. Oh, later, okay. Okay, so they will be from him, but I'll take advantage of, your happiness, I hope. So Professor Farouk did an amazing job this morning, introducing a little bit to the fuel and the kinetics. So he somehow, just lead the way to my talk this afternoon. So before I start, I want to mention, I want to do my acknowledgement, and they are vague, but all the people that have been in my group, they couldn't, this work will not have been possible without them. I have one of my students here, and actually he's now responsible for some of the simulation that I'll show you later this afternoon. Support that I received over the years from different agencies in the United States, so from DOE, NSF, Air Force, or the Army. And then a special thanks to 5 people who sent me a few slides for this presentation that I leveraged, and I'll be very happy to show it to you. So Professor Danna from Italy, Houston Miller from George Washington University, Paul Roney from Southern California, Professor Wong from Stanford, and Charlie Westbrook. But I think many of you know as the previous president of the Combustion Institute. Okay, so this is the agenda that I was thinking for today, and I think it might be a little bit flexible depending on how much you fall asleep or you're interested in what I say. So we'll talk about fuel and some chemistry, especially for the surrogate. I don't plan to bog you down with a question, math, or a lot of chemistry, but I want to give you a glimpse of what is the thinking in this area at this point. And then we'll move to the formation of aromatics, nanoparticles, and soot. And then I'll try to present the material with the perspective of what really we don't know. What are the problems and what the community maybe should think about as we move forward in research in this field. And so for tomorrow, I was thinking to talk instead about one of the topics that I have to say they are very dear to me in this moment, that is the health effect. And so once we have these emissions, how do they interact with the body, for example? What are the risks that we are exposed to? And we might have some exercise for you on some of the topics that I presented today. But it will be just fun, so nothing serious here. So before we move forward, this is one slide that is just a cartoon, but I want to tell you that the type of work that we do is at this level. So we are not going to talk about, there is a reaction. No, there is an atom that looks like this. So we're going to define a species. It's atoms bonded in some ways, and we're looking at how they are going to evolve over time. Okay, so far, throughout the week, we heard a lot about, from very applied systems to fundamentals experiments like this morning. There were always some common themes that were present. And so, there is a need for energy. There was a clean combustion, emissions, dealing with real fuels. This morning, Professor Farouk also highlighted the needs for energy. And then there was some discussion also about the reactions, first with the Professor Im talking about the CFD simulation and the type of information that we need to provide when you run a fluidodynamic code, as well as this morning for the simplified experiment that you can carry in a lab. So you have all those information. What I'm trying to do with this talk is just to say that if we approach those questions with the fundamental approach, we can provide some insightful concept that could be then linked to the applied system that you have been exposed so far. So let's start from what are the drivers at this point. So computational modeling in combustion has received a lot of interest lately. And it's becoming more and more, if I want to say, a hot topic. And there are many drivers for that. Of course, there are some of those that Professor Farouk mentioned this morning, like the societal need. And at this point, with the different scenario and environment that are changing throughout the world, the main needs are to the fuel economy, of course, and reduce emission. So somehow linked to the ability to model an engine, since the main use at this point for a combustion is really with the transportation. It's one of the main features for this, for the link with the fuels at this point. And so emissions reduction, the type of combustion that you have. And so even this morning, there was a great talking about, if you have a low temperature chemistry, what happened to the fuel? What if you have a high temperature? How does regimes change with the fuels? And what kind of product do you form? And so the connection, there is a need for a connection between the engine performance and the type of fuel that you want to use in your systems. At the same time, there has been a lot of advancement in high-performance computing. So if you think about fluidodynamic code that you need to run, which that is very demanding from a computer simulation point of view, then now you can look at a system and try to reproduce with more accuracy. So you can add more chemistry, maybe more physics. So you're moving towards a more realistic simulations. Okay, so those two, one more societal and the other one more really practical, like algorithm, high-performance computing, are really bringing us to study the modeling of this process. The goal is eventually to help the experiment or show some synergy with the experiment. So in principle, if you have a predictive model for your system, there should be a limited need to run millions of experiments. And also the type of experiments could be more targeted towards the question that you have. So let's talk about this fuel and engine that are, I say, the main drivers for the interesting computational modeling at this point. So as was mentioned this morning, fuels, they are material that basically, once you combust, you take the chemical energy that is in the molecule and you transform into heat. And so what's really important is that the chemistry in this system. And so what are the reactions that happen, how the environment changes those kind of the outcome. And again, there were examples this morning. So one of the main applications, of course, of this fuel is, and the reason why people are so much interested in fuels is the high energy density. Okay, and so here I just brought an example. If you look at diesel fuel, that has 4.6 megajoules per kilograms, versus, for example, if you look at batteries, then you have 0.56 megajoules per kilograms. And so, for the same amount weight, there is a huge advantage in using, a liquid fuel like a diesel. And so they are very convenient, especially for transportations. Yes?
That number is 46.
4.6, 46.
46.
Okay, that is one dot.
And the only reason I bring it up is just to emphasize that the difference between, or not the difference, but the ratio is now 100 times, not 10.
Okay, so I just mistyped it. Yeah, thank you so much.
But lead-acid batteries are so far away.
Yeah.
Yet I have to add one more reason. Is the reason lead-acid batteries are far away is partly the lead. The other reason is the battery has to carry its own oxidizer.
Yeah.
But anyway, the ratio is 100.
So, it's the cube. You're talking over kilograms, right?
No, it's 46 megajoules per kilo.
Per kilo. Okay. Okay. So
46 megajoules per kilo. Okay.
So, we're interested in taking these fuels and use for transportation. So, just to follow up on, and I was not, I didn't plan this, but just to follow up on the comment that we just had here, I want to talk a little bit about some alternatives. So let's say that you're not interested in this. What are the alternatives? And so here comes the comment about the batteries. So I want to, at this point, looking at alternatives, but also emphasize that at the end, you will really be interested in fuel and internal combustion engine. So that's the driver. So 46, here is correct, you see? Sorry, there you go. Okay, so as rightfully he was mentioning that, so gasoline. Okay, let's talk about gasoline. Gasoline has a 4, and those are back of the envelope calculations. So stay with me, and I'm sure you will correct me if I did a mistake. So gasoline and other hydrocarbons, more or less 4.6, 10 to the 7 joules per kilograms. Let's take internet data. Okay, so it's a Chevy Bolt, and I have a lithium-ion batteries. So I noted 60 kilowatts per hour. And assuming that is a 960 pound, that's the weight of the batteries, then I will get 5 10 to the 5th joule per kilograms for this battery. So even if I consider a 30% efficiency, for example, in the gasoline, versus 90% that I can have for the batteries, gasoline has a still 29 times higher energy per weight than batteries. Okay. Goes to his point again. And the other thing is that 1 gallon of gasoline is more or less 175 pounds of batteries for the same energy delivered to the wheels. There is also a component that is the recharging rate. So you have 7 kilowatts, if you recharge your home, for example, or 85 kilowatts if you have a Tesla supercharger, versus 5,000 kilograms that you can get for a gasoline pump. So if you look at these numbers, just again, as order of magnitude, you can see some advantages for this. Plus, the batteries, there is some economy. So the cost of the battery in bulk, if you think about money, it's always a good driver. So $500 per kilowatt hour. So if I have a lifetime in which I have 1,000 charge and discharge cycles, I have a cost per electricity that is going to be, at least those are numbers in the United States, so $0.1 per kilowatt hour. And so currently, a battery cost is 5 times the value of all the electricity that will store over its entire lifetime. Okay. So not only the power, but also in terms of the cost. So this is one alternative. The other alternative, if you want to talk about batteries or electrical vehicles, is the Tesla. So the Tesla is a different strategy, right? It's a performance car, and excelling acceleration, and it's cool. It's different than, And so the cost, again, in the United States, more than $81,000. And so I have 85 kilowatts per hour of batteries, okay? And so what they call free electricity at their charging station, Okay, so that's what you get with the Tesla also. And so the value, again, back of the envelope calculation, is $8,570, basically, if I assume that. And so as option, you have that to replace the battery after 8 years is only going to cost you $12,000. So this wipes out even the free recharges. So again, not only power, but also with the other things. This is something that you want to keep in mind in terms of the cost, but also the performance of those batteries. What could be another option? So you don't want to talk about internal energy or combustion engine, solar car. Okay, that will be another thing for transportation. And again, those are back of the envelope calculation. So if I have a midsummer solar flux, I computed 1,000 watt per square meters. And so if I have a gasoline engine with 30 miles per gallon, assuming 60 miles per hour, I have 64 kilowatts. Okay, I did the math to make sense. And so what you need is a 60 square meter collector, basically lots of air drags, if you think about that. And then what happens when you do underpasses or nighttime or bad weather? And so, things that you want to keep in mind. The other option, and I'm talking a little bit broadly about the energy here and the needs and the transportation, if you want, is a solar thermal electric station. This is Ivanpah that we have in California. And there are 3 towers. There is some land that has been used. And so if you do some math here, the maximum power out is 400 megawatts. So when you think about coal or nuclear plant are 1,000 megawatts. So power again, so you have to compare the numbers. And there is also, of course, a capital cost invested in this. And so I have $18 per watt versus $1, for example, for a gas power plant. Okay, and then there are some issues about the environment. But again, power and cost are the 2 things. The other option is biofuels, and we are all interested in biofuels for, the reason is the emissions also. And they are essentially what they define solar energy, so free if you want, but there is some energy required for planting, fertilizing, harvesting, and so they are very land inefficient in some way. And so there are, the life forms convert less than 1% of the sun energy into material, basically. We still have a mandate to replace 37 billion gallons by 2022. But so there will be displacement of other plants. And so, there are issues about the food and biodiversity. So I guess the point here is that none of those is the silver bullet solution at this point. So everyone has his own pro and cons. But still, if you keep talking, if you keep going with me and this thing, the last thing that I was going to say is nuclear. And so, yes, high energy density, since this is one of the things that we are interested in. I was talking before. But I think you can derive the concern at this point for this nuclear thing. So all this to tell you that there is a need for energy. When you talk about this, you need to think about not only powers, there are costs, and of course there are also environmental issues. So in summary, I would say that it's very hard to beat the liquid fuel internal combustion engine. And this is true for power to weight and power to volume of the engine. And so the energy per weight is 4.3 10 to the 7 joule per kilograms, and the energy per volume of liquid hydrocarbon fuels, basically. The material cost, it's low, if you think about this. So steel and aluminum. If you think about fuel cell, then you got high prices with the platinum, the batteries, the lead, and of course distribution ending. So those are all factors that come in when you think about this. So bottom line is that we're interested in fuels, the synergy with the engine, because in this moment it's the best scenario for the energy, and the needs for transportation. And so at this point, we need to look into ways to study this process that are a little bit maybe more based on the computational work, always in conjunction of work with experimental. So I just want to mention that there are practical alternatives to this. So natural gas is one of those. And there is issue, of course, with the greenhouse emissions. but they are 4 times cheaper than electricity, 2 times cheaper than gasoline or diesel for the same energy. So those are just an idea. Those are practical alternatives at this point. Another one is the Fischer-Tropsch fuels, and you heard this also throughout the week. But we can use biomass instead of coal, for example, as energy feedstock, so to reduce a little bit the emissions of the gas. So none of those, again, is the best solution, but you have to compromise. So things you need to understand. Before, I think you design, you think about engine and you want to design the zero emissions solution. Or maybe you want a car that is 100 miles per gallon, 1,000 horsepower engine or something. And then at that point, you make so much money that you decide to retire. And so when you talk about engines, the room for improvement, I would say, is a factor of 2, right? So if you think about Carnot, Otto cycle, if I have an engine that has a compression ratio of 9, the maximum efficiency is around 55%. And so real engine right now is about maybe 30, okay? And so the differences are, of course, the losses, the heat losses, the friction, the resistance, so there are many of those. But if you think about pollutants, and so looking at the chemistry of the fuel in the specific environment, then there is a huge room for improvement. And so pollutants are non-equilibrium effects. We'll talk about this a little bit today. And so what happens is that instead of having the fuel, pure air, you're going to produce not only CO2 and water, but a lot of hydrocarbons, combustion byproduct. And so they can cause a huge drop in efficiency of the engine. An example, and I'll talk a little bit more later, is that the filters for gasoline, for particulate, and so they degrade the efficiency of the engines. So bottom line of those introduction a little bit is that we are interested in fuels in conjunction with an engine. It's really the chemistry, the modeling, they are key actors, players in this scenario. So what we are looking at is really a tool that can be predictive. We're changing the environment. We're changing greenhouse gas reductions, renewable fuel, synthetic fuel. Those are all new areas of research. And so how engine depends on the fuel is something else that we want to investigate. So if we can make some quantitatively prediction of the system, then that will improve decision-making, for example. They will reduce the need to run experiments, but also will bring the solution to the market in a shorter amount of time, if you want. So what I say here, accelerate innovation. Okay, so the issue of fuel and engine is really important. And just to highlight this, currently there is a big effort in the United States, supported by the Department of Energy, to look at the optimization of fuel and engines together. It was a DOE effort. And so not only to investigate what are the advanced engine design, but also fuel property and how the synergy between the two could be leveraged for the systems. So this is the Co-Optima. It brings together in the United States 9 national labs, 13 university, government, and industry. And the question is that, what fuels engine want? Not only with the short time frame, so, having the current fuels, what could be the best one for our engine, but also in the future, what fuels can we develop that could be the best for the engine? And so what's on the left, that is from their report that just came out a few months ago, is that so the fuels, they're looking for fuels with targeted properties that can enable higher efficiency in the fuel economy. So keep this in mind, because what I'm looking right now is the properties of my fuel, my molecules somehow. And so also try to leverage different feedstock. And so for the future, maybe design something new that could be produced in high quantity. Okay, so let's see how we can start talking a little bit about the modeling of this fuel. So going back to what was presented this morning. So real fuels are very complex. And here I'm highlighting 3 of the major fuels. So jet fuels for aviation, and then diesel and gasoline fuels. And the point of this graph is to show you that the distribution of compounds inside is different. So if you look at gasoline, you will have hydrocarbons that are smaller than you can have, for example, in a diesel engine or the fuel. And so gasoline usually has an average of 8 carbon. So as a molecule, the average molecule has 8 carbons, while instead you look at a JP8, the distribution is shifted to the right, and the molecular weight is much higher. So as 180 is the molecular weight of the JP8 versus 110 of the gasoline, for example. So there are different compounds inside. Now, who cares? The problem is that these compounds play a role in many phenomena. And so our goal is to try to understand what happened and how they do that. So if I want to show you a similar graph now for gasoline, just to narrow down on one example. Before I was showing you the average mass that you can have. Here, instead of showing the distribution. So when you have a gasoline, you can see there's a pie chart. And I don't know if any of those words make any sense to you, but I try to show you on the left some example. So what I'm saying for the gasoline is that the blue part, so of alkanes, it's really, it's one of the main contributors. It means molecules that look like the first two here on the left. But then there is also a high contribution from aromatics. So something looks like a benzene, the last on the right here. So, and you can expect that if you start, for example, the pyrolysis of those two compounds, they will behave differently, and they will lead to different hydrocarbons. Not only that, but also the environment in which they are combust will create a different byproduct. If I do the same analysis with the diesel and jet fuels, you can see the distribution changes. Again, I have different compounds in my system that somehow are doing different things once they place in a combustion environment. So fuels are complicated, so we go back to the idea of a surrogate. A surrogate is a simplification of your system. So you identify one or more compounds that somehow target some of your key properties that you're interested in. And as well, you can think that it depends really on the system you want to model. So why surrogates are needed is because, first of all, it's impossible to identify all the molecules present in the fuels and their composition. The other part is that the information on the combustion modeling is not available for all the molecules. So if we get like a weird molecules, there are no mechanism available at this point. And the third one is that the computational time, if your goal, for example, is to run a simulation like Professor Im was showing the other day with a CFD, you need some gas phase chemistry, or like this morning also. That's impossible. So computationally, it will be impossible to run simulation when you have millions of compounds involved. So what do we care about this surrogate? The idea is that we want to, the overall goal is, again, to model the fuel behavior in an engine at this point. And so this is just an example of a CFD, simple CFD calculation that we did, nothing compared with Professor Im does. But the idea is that, I want to put a point, that if I take a real transportation fuels, it's very hard or impossible in this moment to go directly to the simulation. But if I try to go through the fuel surrogate, if I simplify my system, then I have a chance to go back and do my CFD simulation of the engine. So this is a possibility. So the surrogate, the jet fuels. So I want to briefly go back to one of the first surrogate concepts. And this is when I was young, and I was working on one of my first projects that I had here in the United States, actually. So I was working, as Mani was mentioning, for one of the 5 ASCII centers that the DOE awarded a few years ago. And one specifically, that one was in Utah, and the idea was to predict, so computational, the idea was that the fire and explosions. So once you had in a pool fire, I think there was a question this morning also about, so once you have a pool fire, and let's say that there is a container with a high energy material, how long it will take for the explosion of the tank, and how violent will be the explosion. So there were a lot of people involved in this project, and I had, my small role was to look at the formation of soot, nanoparticles in this kind of scenarios. And by the way, I want to mention that I think that was a great idea, a great experience for me, because really was a highly interdisciplinary. And so I think, as you will see throughout my presentation, this is something that I really value. So not really focused on one topic, but just trying to be a little bit broader in the interactions and the needs. Okay, so we were talking about jet fuels in that case, and the idea was to reproduce the behavior or some combustion for those fuels. And so at that point, JP8 is very complicated, so we had to narrow down the property that we were interested in, as well as the description of the compounds in our system. So we were interested again in something that looked like this. There's a pool fire, and then the container with the high energy material, and so. So when you want to talk about a surrogate, what is the idea? And I'm going through this a little bit quickly today because tomorrow I'll plan to, interact a little bit with you on this topic. So how do you determine the surrogate composition? So there are experimental approach, and there are also computational approach. So when I talk about experimental approach, there is a knowledge, and there is a trial and error to find the blending ratio, and then it's comparing the property or the combustion behavior of the real fuel versus your surrogate, your mixture of small molecules. Computationally, there is the optimization method that have been published in the literature to find the mixture that matches the real fuel, basically. So I'm going through this historically, and I might have skipped someone, but I just want to show you that this has been a really interesting research area, and many people have looked at this for different approaches, including Professor Sarati here. He's co-authoring a couple of those that I'm going to show you here. So this is the one I just mentioned, and so that was for jet fuel, and that was the fuel pool fires. We came up with was an experimental approach. So the way we identified the mixture was experimentally, but then we look at the chemistry. We're able also to compare with some experimental data. So you don't need to remember the molecules. I just want to tell you that what is the interest here. So there are other people that have looked at this, Dago in France, so jet fuels behavior, again, but he was more interested in autoignition characteristics. More work for jet fuels again, but sometimes now looking at different properties. So it was an extinction and autoignition limit. This is from the San Diego mixture. There was another surrogate that came out. Then we have the Haken surrogate that is also for jet fuels. Again, trying to look at the extinction and autoignition limit in non-premixed flames. And then work for Jet A, so another jet fuel, surrogate jet fuel. And this is from the MURI. That was a huge effort in the United States, so a multidisciplinary university effort. And so they also have some experimental data, but together with some optimizations of the property we're interested in. This is one for the gasoline, which Professor Sati is one of the co-authors as well. And there were more for gasoline, so depending on the system that you were interested in and the property that you want to target at this point. And you heard everything about Ron this morning and on. Okay. So this is one of our latest approach on surrogate, and I want to spend a couple of minutes just to say that this was, again, driven by a need. In the United States, there is a single fuel policy. So over the last few years, the Army decided to standardize the fuel, so using JP8 as a primary fuel for all the air and land forces. Okay, so the result of this was that we have to take a jet fuels and put in a diesel engine. And so the ignition engine needed to go from what it was a DF2 before for a diesel to a JP8. Okay, there were many benefits, so that's the reason why they did that, including the corrosion, the water entrainment, the nozzle fouling. So those are all practical needs. But for us, what that means is that if you look, for example, at jet fuels. Even within the same jet fuels, there is a huge distribution of cetane number. So you heard this morning about the cetane number. And so those are 3 jet fuels right now. So Jet A, IPK, and S8. So those are the synthetic jet fuels. And what you see, I guess the point I want to make here is that the cetane number changes dramatically between, you can go from 30, 25 to all the way to 60. And so your engine now needs to be able to deal with this. And so the question is, once you have those, how do they behave in an engine? So the first thing that I want to mention is that we need to go back to the chemistry to maybe try to model this scenario. And so the two peaks that are here are highlighted is that similar isoalkane content, but those two fuels have different cetane numbers. Okay, so the isoalkane is not somehow driving this cetane number. What we know instead is that the cetane, if you look at the C8 linear alkane isomers, so if I go from octane, that is linear straight, I have a cetane number of 64, let's say a DCN of 57, and then if I branch, I have a branch compound, then I can go all the way to 52, but also to 14. And so the question is that the highly branched, they have a low cetane number, and the lightly branched, they have a high cetane number. So just having compounds that are different in terms of the structures will cause a different chemistry inside the engine, and therefore, a different cetane number. So we worked on this project for a while, and the idea was to help, again, to try to have jet fuels in a diesel engine. We came up with an optimization technique, and so is a surrogate optimizer, and the idea is that you have some properties, then you look at the composition, at the mixture properties, and then run the optimizer, trying to match basically the real fuel properties. That's the overall idea of optimization. And so for us, what we were interested is in different properties. So not only the cetane number, the lower heat of vaporization, the hydrogen-carbon ratio was interesting for us, the molecular weight, as well as the density, viscosity, distillation, and surface tension. And our goal was being jet fuels. So we worked over the years, and we came up with surrogates that, using basically those 6 compounds reported here, was able to reproduce the 3 of the jet fuels that we were interested in, of course, changing the relative concentration of the species. Okay, so and just to give you an idea of the experimental data, that we compare our solution with the experimental data. So this is the liquid. So first of all, over time, over temperature. So we are not looking at a property at a fixed point, but we're looking at distribution over time. And so the liquid density and the viscosity and the specific heat. And so what you see here is that our surrogate, there will be the line, how it compares with experimental data. And actually, even if you're running, over a temperature range, the surrogate is doing a pretty good job with all those properties that we're interested in. So I just brought you an example. This is a kind of a sensitivity analysis, and the choice of the property is really important when you design a surrogate. And so if I compare the result I just showed you, in which I have 8 property that I was targeting versus only 3 of them, then if you look at the results here, so running the optimizer in different conditions, I will have a distribution of the compounds that is completely different. So here is, with my 8 property, the bottom panel is only with the 3 of them. So, of course, you change the compounds and the relative importance of them. And if you do, for example, just an analysis on the property that I was showing you before, this is the one with the 8 property, complete set. And this is the value that you get once you match only 3 of those, for example. This is for the density, but also viscosity also. So when you look at surrogate, you want to be careful about the property that you're interested in, of course, the application. So why we care, again, we go back to the initial concept that when I have my combustion simplified, so I have to follow 5 compounds instead of hundreds, then I can start doing some simulation. And this is just a simulation that we ran for the liquid penetration in an engine, showing that with our surrogate, we were able to capture the difference between the Jet A and the S8 that experimentally are found for them. And so you can see that the distribution here changes with the chemistry that we found. Okay, so let me summarize a little bit what has been done. Oh, that's weird. Oh, it's not showing the page. there is a summary with some words here that I don't know why it's not showing up. So you just trust me, I guess, at this point. So I'll leave with this picture. And so the surrogate are some mixture of hydrocarbons, usually. It can go from 1 to few. The idea is that you don't want a huge number, of course. Otherwise, you get in the same trouble for the simulations. And they enable simulations of transportation system at this point, so fuel for transportation. The target property is important, and the component selection of the surrogate is also determined. And then you need to decide what is your method that you want experimental and optimization process. Okay, so this is what is available. I want to go back to the idea that I was showing you before. So the fuel engine synergy. So what fuel property do we want? So why I talked about surrogate so much? Yes, there is a need for simplify the chemistry, and so surrogate is helping. But I think all the research that is going on can be augmented, especially the surrogate definition with the recent data that comes especially from this effort. So let me go back to this DOE effort, the co-optima, that I was showing you before. And so the questions are, what fuel do engines really want? And so what is the key fuel property that impact the efficiency? And at the same time, what fuel should we make? So the two questions I was talking about. So maybe one is more short-term, the other one is longer-term. And if you think these answers can help you define a surrogate as well. So the team within this co-optima, as I was mentioning, recently published a report. And they define a merit function. That is still, there is empirical contribution, is still at the beginning, is in infancy. But the most important part for us in this talk is to see what are the properties that we want to focus on. And so what molecules or functional groups give a desired property for the highly efficient engines? That's the question. And so there are different contributions. I see 6 of those, and some of those have already been discussed this morning, so I'm not going over that. But the idea is that the research is framed about the efficiency of this merit function. So what are the most interesting players in terms of property for a fuel? Okay, and so I want to highlight 2 at this point, the octane sensitivity, that you might have heard already, and the particulate. Okay, a couple of things, again, where the chemistry comes in. So without repeating what was said this morning, let's go for the merit function. S, the octane sensitivity, so OS, you will see here, it's an important parameter. So fuel octane is a measure of the knock resistance, as was said. And so if I define the octane index as RON minus Ks, S is the fuel sensitivity, so RON minus MON, so we did this morning, and K is an engine-dependent constant. So increasing the octane index enables the engine compression ratio to be raised, if you want. So this morning also, Professor Farouk was basically telling you how experimentally, you can determine the RON and the MON of a fuel. And so the only point I want to add is that the 2 tests interrogate different reaction conditions. So there are fuels that have the same RON and MON, but there are fuels that they don't. And so let's see what happens. So octane sensitivity, that is the one in the merit function, is basically the difference between RON and MON that you can have. So for some fuel, OS is as large as 10 or 20. So the current trend in SI engine at this point are basically improved efficiency by increasing the compression ratio or turbocharging also. But this can cause knocking, right? And so since the engine autoignition delay times decrease and the cylinder pressure increases, the reason why people got interested in this octane sensitivity is that could fuel with high octane sensitivity can be interesting for those scenarios. So here I'm showing you some very recent result. This is a paper from 2017. And so fuel with IOS, so OS, show better knock resistance at high load condition, and so maybe are beneficial for higher efficiency. So if you look at, I'm looking at 3 different fuels, see the bars, 3 fuels with the same RON, but different octane sensitivity. And so isoctane, gasoline, and E40. And so low load, they have similar knock resistance, but as you increase the load here, they get a better knock resistance at high load for iOS fuels. So this is a pretty new concept, but the idea is that we want to go one step further and look also at this characteristic in the function. So Westbrook, for example, has done a lot of work recently on this, as well as Professor Sarati. But one of the comments I want to highlight here that the small molecules, for example, have a high OS and low temp and almost no low temperature reactivity, because the small size make impossible for them to support the radical isomerization that was discussed this morning. So one of the reasons for that, again, you're linking the structures of the molecules to the type of reaction and therefore to those more macroscopic parameters like OS. So the bottom concept or the message I want to deliver is that the combustion chemistry is important. So even if you want to talk about this merit function that starts from very applied or empirical evaluation, then going back to the chemistry is driving the research at this point. So the other component of this merit function was the particulate, and this is something I want to discuss a little later. And so the need for this type of research is that the gasoline degrade engine efficiency. And so I think you guys might all aware of that, but you have an increase in the back pressure in the exhaust, so higher pumping losses and greater potential for knock. So in summary, with this brief introduction that I made so far, I think what is now important in the combustion community is this quest for models that are capable of numerical prediction, of course, with quantifiable uncertainty. So the idea is, can I become so good in my simulations that I can predict what taking a fuel will do, for example, for an engine? And so what I mean by predictive is also that it's a model that can reproduce a set of well-defined experimental data, but also be able to predict what happened outside the boundary it was defined in. And so not only for the known conditions, but also for the unknown. So it's a little bit tricky here. And if we think about this scenario that I just showed you, one of the rate-limiting steps is really the chemistry. So the surrogate, you can narrow down, you can get 5 compounds, but then from that point, from the surrogate to the chemistry, to the CFD, it's another leap, because the chemistry is really the limiting step here. And the reason why, because the knowledge is not complete, not only in terms of pathways that can happen, but also, of course, as a measurement, but also theoretical simulations of the systems. So what I'm going to do next is basically tell you a little bit about what is now available in terms of the chemistry, and once you have a fuel, how you form aromatics, and then eventually those nanoparticles that I think many of you might be interested in. So before going any further, I thought we can take a break now and then dive into the aromatic chemistry with the hydrocarbons. Okay? Is there a question? Okay. I think there's a question. I don't know.
Thank you, Professor. I have this question. I often ask myself also, because I've also been there in this field for many years. I actually do not completely believe in the economics that you showed just now. And I believe it is more local than it is universal.
Absolutely.
For example, USA and Saudi may have different story than India and China.
Yes.
And that can actually put more focus on fossil or completely derail also. Mm-hmm. So I'll give you an example. For example, now they are talking about the levelized cost of energy. It's not like just comparing the fuel cost or the cost of operation. So in that terms, how do we fare in levelized terms of cost of energy? And since the renewables and alternatives are costs are falling faster than anything else. Do we see the same story 5 years down the line, 10 years down the line? Because countries which import petroleum, they don't want this story to be true.
So I do agree with you. I absolutely agree with you. And I think I mentioned before that this analysis was really at back in the envelope and more related to the United States. Yeah. And I agree that as you move in the, towards the world, the needs are different. And the sources available are also different. Political drivers are different. So I do agree with you that is somehow a local need.
Right.
And as we move forward, absolutely.
That
was not my intention to say that this is true all over the world. Also, some of the numbers were really in dollars, so like, yeah. Okay.
No question? Tony, okay.
Oh,
so this was just a great sort of view of how to meet many parameters with surrogates, and I haven't seen it done any better, so that's awesome. My question relates to sort of second-order effects. So one of the issues with fuels can be things like coking deposits and carboning, and how do we think about that in the context of surrogates?
I'm sorry, how do we think about what?
So second-order effects as it relates to engines and fuels, things like carbon deposits,
yes,
coking, those are also serious reliability problems, if not,
absolutely,
under well-controlled situations. How do you think about that when you think about surrogates? Do you see a day where we could include that in the discussion, or is that a separate thing?
That's a good question, actually. So right now in the surrogates, we don't take into account those. I can imagine that not now, but if we can understand exactly what are the mechanisms that drive this type of interaction, then we can trace back to the fuel characteristics. But I do believe that exactly for what you mentioned, maybe some modeling, maybe some mechanism understanding of what happened, why you have those deposits, for example, what is the quenching or something, could be really useful. So it's not something that we're doing right now, but I can think ahead and maybe include that in what I call second generation, third generation of that.
Yeah, so for those researchers, carbon deposits is an area of we don't understand very well. It's
right,
very complex.
Yeah.
And maybe we're thinking about surrogates would be a good motivator to untangle some of
right,
those complex business.
Yeah, we are not there yet, for sure. And really what you saw today with this merit function is that at the top of the, the heart in terms of development, as you saw, including, emissions, particulate, but not the secondary effect. But it's a great point, absolutely, yeah. Yes.
Quick question.
Yeah.
In your surrogate formulation, how do you try and approximate the cetane number? Like the rest are more physical, but the cetane number is more arbitrary.
So this is a great question. So that's one of the criteria that we think about when you choose the compound. So the surrogate, you cannot choose whatever you want, okay? You need to choose something that is available. And this goes back to the short-term development. And so when we choose now our 4 compounds, we make sure that those compounds have a cetane number reported in the literature. So that's a great question.
Do you buy molar, for example?
Yeah.
Oh, okay.
And so this is actually a huge constraint that we have. If I don't have the cetane number, I cannot do the optimizer, or I need to give up one of the properties. So.
All right, why don't you get some coffee and we'll be back in 10 minutes? Is it still a deal?
Mm-hmm.
Okay. Yep.
So welcome back from the break. There will be one more break. I want to go over now some concept about the mechanism. So we want to talk a little bit about chemistry. And so what do we know about the fuel behavior in a combustion environment? And then I'll promise a break, the next 45, maybe 50 minutes, and then we'll wrap it up with a session more on nanoparticles. Okay, so I guess everybody's happy for the price. So you will have will be more available to listen to my chemistry at this point, I hope. So let's talk about some basic definition, okay? So first of all, we heard about chemistry, we heard about some rates throughout the week ago also. So first of all, a mechanism is, what I think is a mechanism are the pathways responsible for a phenomenon, okay? And a model instead is a set of mathematical equations that describe the phenomenon. So those two things sometimes are confused when people describe the chemistry of that. So given a set of elementary reactions, that could be, for example, a mechanism, we need to specify the equation for the system that we are interested in, the PDE equations, so the mathematical model. And then basically the model that you have, so this elementary reaction will be used to define the behavior of the system. Okay. So mechanism, pathways, model is more related to the system that you're interested in. Okay. So when we talk about kinetic models, we're talking about a list of reactions. And so as you heard already, there is a law. So there is a how fast this reaction will go. And that's characterized by parameters. And that's usually what the problem is. So the adequacy, right now, some people come up with reactions, and then they somehow list the rates, those parameters. And then what's the normal protocol right now is to assess the adequacy of a model, basically, by comparing with experimental data or, other maybe model predictions somehow. And so this has been started with developing this detail mechanism. And so there is this idea, what they call comprehensive detail mechanism, if you want. And so the way they are built is a kind of a hierarchy. You have a core, in which usually is the hydrogen oxygen that is common to all the combustion system of hydrocarbons that we are interested in. And so there is a set of reactions that we develop for the hydrogen oxygen, and then they validate against experimental data. Then what you do, you add the complexity. And so you start adding the chemistry of the first hydrocarbons, and then the second, the third, all the way to, component of the surrogate that we saw this morning, that can go all the way to C12. So think about that. You have initial hydrogen, oxygen, and then you add the complexity on those. And so somehow there are constraints that you impose if your system is changing by one. And what I mean by that is that combustion is a really complicated process. So the system, the chemistry isn't intertwined, and the dynamical behavior, it's coupled. Okay, so you have different systems evolving at the same time, and their response is somehow a function of what's happening overall in the system. So let's think about hydrogen oxygen. That is very simple, and even the simplest fuel, we still don't do a good job at representing the hydrogen-oxygen chemistry. So the overall reaction is, two molecules of hydrogen plus oxygen, and they form two water molecules. But the chemistry, of course, does not occur in this one step, and there is a multi-step process. And so each step, and here I have just an example on the right here. So those are 10 of possible reactions that can happen. They are single steps in which you define the reactant, the product that you have, and eventually you need to assign also a rate, and as well as the thermo, for example, or transport if you're doing a system that is more complicated. So, and then the rate for each reaction is determined by the rate constant, that the law you introduce, and the concentration. Okay. So some important reactions here are listed, but even for a nitrogen-oxygen, and I think that was one of the questions in the test this morning, even for a simple system, you don't have 10 reactions, but you have more than that. Okay. How many do we have? Who got the prize here for this question? How many? You got the prize, guy. How many? 19, yeah, okay. So I think the winner was that 19, yes. So even for those systems, it's not one step, so you have a multi-step. Now, the other thing that I want to describe before we go forward is that this is, I'm simplifying things here because the point is to give you an idea what's happening, not just all the math. So usually when we talk about reactions, reaction constant, one thing to think about the process is looking at the potential energy. And so species, there is what they call, there are valleys between species. So species is something that is spent times enough in one of those well. And then there are dividing surfaces that basically connect to different wells. And so the rate, when we talk about rate, so this is, let's say, the landscape that this particle, so you have a molecule here. Once you put it in an environment, it can react. So it can go over here, but it can go also on this side, and it's function, of course, even of the height of the barrier. So when we talk about Arrhenius expression that you saw before this week, and it's basically talking about A, N, and E, I think you saw that, activation energy. Basically what it's saying is that if I go back to my atomistic description of conditions are very intertwined. So if you have a simple fuel plus air, think about a natural gas, at room temperature, the mixture is stable. If the temperature is low, but you increase, but it's still relatively low, then you start forming aldehydes and peroxide. If you increase the temperature and you are moderately rich, then the reaction form, for example, syngas and CO2. H2 and CO2. And if you get richer and richer, then you go to form acetylene, benzene, particles, and soot. So the fuel and environment around it really dictates, what's happening to your byproduct. And the point I was trying to make with the first part of this talk is that our need is driven by, applied scenarios like, the engine or the transportation. But really, all those more macroscopic processes can and need to be addressed maybe by a deeper understanding of the processes. And so combustion chemistry seems to be a key, a common thread among all the processes that we have seen so far. So, and here again, I'm doing this overview. So when you have different fuels, they make different, for example, alkenes. Okay, so we're interested in that. So the main alkene that you, is a C2H4. And I think many of you heard, and this morning as well. And so in absence of O2, he goes to acetylene. And acetylene is really important for the soot. I will show you later. The second most important alkene is the propene, so C3H8, something else that you form. But the reason why it's interesting, and you need to track that, is that it will go to C3H5. That still doesn't mean much to you, but it moves farther to C3H3. And now this is a key player in the soot formation as well. So somehow, once you put two C3H3 together, you have a various addition reaction also that include acetylene, then you're forming aromatic and soot. Okay. So without going too much into details of all the compounds, I guess there are a few concepts I would like you to take with you as we move forward. The fuel and the environment dictate the byproduct. Some of the key players, if we look here from the beginning, so I have the formation of this gas phase, alkenes are the key players. And the reason why, because you go to acetylene, that is important later for soot, as well as radicals like C3H3 that basically contribute to aromatic. So somehow, if you could, from the beginning, different fuels will have a different distribution of the alkenes at the beginning, and somehow you can correlate that with what's happening next. Now, although some of those pathways are clear, to the community, you still have different mechanisms in the literature. And what I mean by mechanism is that we have different research groups that will take, this is my fuel, and those are the byproducts that I form. So basically, you can have multiple models that have been created for the same system, but they have different numbers of species, different thermodynamic and rate parameters. And so this brings to this kind of graph that Professor Him also showed the other day, but it just gives you an idea of the magnitude of the problem, if you want, at this point. And so this was published a few years ago, and I guess there is definitely an update right now. But it is that we are now looking at this number of species, at this number of reaction. If, for example, we look at C10, C12, they were one of the component of my surrogate. So remember, my goal is take a real fuel, develop a surrogate, so I can narrow down my chemistry, let's say 5 molecules, but still, for each of them, I need this. I need to develop my reactions. So think about 5 molecules, and now for each of them, I have on the order of 10 to the 4th reactions. So it's going out of control, I think. That's what. And so let's see what's happening in this mechanism. So to simplify the problem, you take the fuel, you take the oxidizer, and this is really just to give you an idea what's happening. And once you get to the flame front, this is the gas phase mechanism that you saw in the plot before. So I'm talking about only gas phase, okay? So look at the formation of basically CO and CO2, but also all those unburned hydrocarbons. So this guy here is for the gas phase only, okay? So only this step will take a 10 to the 4 reaction for this. Okay, so we're back here. The problem is that once you have those unburned hydrocarbons, as I was mentioning to you, like acetylene or ethylene, all those are key players for what happened next. And so to this 10 to the 4 reaction, you need to add the aromatic in the gas phase, because now you have the precursors and you're forming benzene, the first aromatic. You're also forming those polycyclic aromatic hydrocarbons. And then what happened to these guys? It's totally another world, because then you transition from the gas phase to particles dynamic. So you start forming the first particles, nanoparticle, that eventually will grow into soot. So as you can say, the complexity is increasing here. So let's, I want to tell you a little bit what has been done for the formation of aromatic. So I'm going to look at this one here. So the aromatic, the gas phase, and the benzene. This is a really important step, because if you can see here from this kind of arrow, those are the precursors for what happened next. Some of the precursors that happen next. And so having an accurate mechanism, that is the base before you move forward to more complex questions, it's very important. So main approaches that have been taken over the years, and I'm summarizing the most important one here, or some of those, usually is done with ab initio simulation, and so try to use quantum chemistry to understand how the molecules behave, and what is the kinetics also that brings them together. So I'm just reporting, you remember the alkenes I was talking about, that they are important, and the acetylene. So when you talk about aromatics, some of the main contribution are acetylene that reacts with what they call a C4H3, but also a C4H5, so different molecules, and they form a benzene. So if you track acetylene, then somehow you're tracking benzene also. So that's the reason why you need to have a good mechanism for acetylene formation. The other one that was interesting was the C3 that I was talking about, the radicals. Once he finds an acetylene, so the two key players there, he forms another C5H5, cyclopentadienyl. 5-member rings, interesting also for the combustion. Those are very interesting reactions because the C3H3 is a radical and C2 is a stable compound. So once they find each other, a radical always react fast. Two radicals, like C3H3, is even faster. And so, again, the C3H3 forms benzene. And this has been a lot of study on those molecules with great people doing very accurate simulation just to look at one reaction and the rate constant. So since we are looking at the aromatic formation, so those are all the precursors for my second part in which I form particles. I just want to mention that there have been a lot of random numbers. There have been a lot of study in the literature. This goes back to many, many, many years ago. And so there have been a lot of people proposing different compounds. So they go from polyacetylenes to ionic species and polycyclic aromatic hydrocarbons was an option. And key species that can influence the second part of the dynamic. And so, but the majority of the opinion, and that's what we follow today, is basically the role of polycyclic aromatic hydrocarbons, so PHs. And here I have just an example on the right. So it's a structure that is aromatic, composed of aromatic rings. And they have been identified as the most valuable, the most interesting precursors for the particle dynamics. So the story starts with 1985, as I say. And again, I'm trying to follow a little bit historically what happened. But the work of Stein, so Stein and Farr, was one of the things I read when I started my PhD many, many years ago again. And I still remember the paper. And what they try to do is to look at the process from a thermodynamic perspective. And actually, I want to show you something later about this, the thermodynamic concept. So they they identify that pH, so the one I showed you before with the 6-member rings, like naphthalene, so 2 rings, or phenanthrene, 3 rings, or pyrene, 4, they are very stable, okay? And so what that means is that if you think about gas phase and species present, then you will form those kind of compounds since they are stable in those conditions. And so what happened is that the temperature plays a critical role in the rate for the growth of aromatics, as well as the hydrogen, because they are stable, they don't want to react. So you need the nitrogen to go in and remove and activate them if you want. So what they look at was the stability of those hydrocarbons between 1500 Kelvin and 3000 Kelvin. And what they came up with some analysis of the equilibrium constant. So they took acetylene and they look at the formation of different aromatics with something that I think is familiar to everybody who has done some kinetic here. Those are the stabilomers. So it's basically the structures of the most stable isomers that you can find in the gas phase environment, right? And so what this has contributed to is the idea of the pathway. So now people who want to develop pathways to go from my fuel or my hydrocarbons, small hydrocarbons, to these guys, they know that eventually they need to end up here, okay? Because this is stable, so eventually you form that. So the thermodynamics drove this kind of study, and now the idea was, can we find pathways that can bridge to those species? And here comes one of the most famous pathways in the combustion chemistry, I would say, for the pH, that is called by the Haka mechanism. So it's pioneered by Professor Franklin at University of Berkeley, but he's been working with many, many people over the years. But the idea was based exactly on the Stein and Farr work. And so he leveraged the formation of acetylene. And the idea was that if you have stable compounds, like one of the I showed you before in the table, then an hydrogen comes in, activate the molecule, because it becomes now a radical. Then an acetylene, that is another key player, will come in and keep growing the structures. And so you will have this kind of repetitive process in which you can go from a small, benzene, for example, that you form, to adding acetylene, then you can close to 2 rings, and then you further acetylene and hydrogen, then you can close to 3 rings, eventually to 4 rings here. Okay, and this is very important compound. This is called pyrene, and will be significant for the growth of particles. Okay, so this was a great work that is still used by people who do combustion chemistry for the pHs. And it really captured the important factors of the molecular weight growth I was showing before, so the acetylene, the hydrogen, but also the temperature. The second contribution, I'm talking historically, that really has changed a little bit the scenario was the study on activated reactions. And what that means is that Dean in 1985, so that demonstrated that chemical activated reaction really play a role. And then there were a lot of follow-up works. So, but how does this work? So what that means is that, again, I want to give you the idea, not the details here of the system. But if you have this, if you have those 2 compounds that they react with each other, it's not a simple reaction in which you go down here to this product, okay? That's not the way things can happen. But what happens is that you can form a compound that is highly thermalized. So it's not in the ground state, it's excited, is an activated carbon. This one here is called C6H7. Okay. And then at this point, the chemistry becomes more complicated. So if you see on the right, the 2 fragments can become this activated compound that you see here. This guy can go back to the reactant. It can go down to a stable form, because you are in high temperature regime, there are collisions, or you can form those products here, for example. Or option number 4, if you want, you can isomerize to this guy that is now cyclic, is an isomerization reaction. And this can be stabilized and go down to forming this phenyl. Okay? So the message of this slide is that the chemistry becomes more complicated. Okay? Excited states and the activated energy can play a role. And they change the scenario, they change the pathways. So now you can consider also those 2 reactants to go to your aromatics that you're interested in for the formation of particles. Same things that happen with the chemistry of radicals. So I was mentioning the C3H3. So radical stabilized free radical, resonantly stabilized free radicals, such propargyl. What that means is that they are very stable So they interchange configuration constantly. And so, but once they react, they are very radical, they are super fast, and they lead to the formation of benzene. So now, in addition to the HACA, that is acetylene and a stable compound, we're talking about C3H3, for example, we're talking about activated species. Now, this has been very interesting work, but really the rate coefficient, when you talk ab initio simulation, they really require details, a lot of details, and so the calculation is to be super accurate. That is a few people who can basically do those type of calculations. Further work, just to move to the more practical side, has been done by Franklak, of course, Wang, and they look not only at the thermodynamics, but also the chemical kinetic. And some of you that work already in combustion in the modeling, you know this for sure, they start putting together this mechanism. So now I have an idea how I can go from the fuel to the oxygen. I need to form those gas phase species that eventually will turn into benzene. And of course, you can have multiple pathways. So one of the first model, kinetic model, it's not the first, but one of the models that is currently used is what they call ABF. So is Appelbocher and Franklak. There was one of the mechanisms developed years ago. And there are newer version. There's one Combustion here, you guys, that you have, that actually we've been using a lot also. And, but the idea is that people are building models. And so the idea is that we need to find a way to describe the fuel and the formation of those aromatics, because are precursors to my particles. So in terms of the chemistry, now I talk about benzene, how can I grow? Because I'm still a benzene. So benzene, you've seen that over the years, people have developed different pathways. The more they know about the chemistry, the more they can compute with the computational power, the more they can add to those mechanisms. When we talk about pH, so 2 rings, 3 rings, more, then also there's been a lot of work that is done, this is more recent before, using ab initio technique. And so the idea is to use quantum chemistry again to look at how reactant can evolve. And so people have recommended a lot of pathways. And here, those are all maybe names to you, but this is showing bigger compounds. So let me give you an example. So actually, this is a work that we did, just to put something from me, in which we were looking, we used ab initio technique for this, looking at, for example, the reaction of 2 C5 molecules, so C5 plus C5H6 plus C5H5. And so what I want to highlight here that, yes, we did ab initio simulation, so we look at the energy of the reactant, the energy, the transition state. So you remember the picture I showed you before with the valley? So you need to have something about the energy of the valleys, but also the barrier, the height of this. And so, but then the pathways increase. And you go, you know, eventually, very quickly, this is going to explode, basically. You have a lot of pathways. So, but for this, what we showed was that these two compounds can react, and they form a very interesting, you know, pH. So the idea is that we need to add some chemistry to develop those models. Those are the energy profile that we computed with ab initio simulations. And for this specific system, we also compare with experimental data, in which they did the pyrolytic growth of a hydrocarbon for C5H6. The other thing that you might have besides that is rearrangement also. So here is still a pathway for pH, so the bigger rings. But we're looking here at the cyclodehydrogenation reaction. So if you have 4 6-member rings, somehow they undergo reactions in which at the end you can end up with, you know, just closing the ring here, and you have a 5-member rings in the center. This is very important because the 5-member rings give curvature to the system. So, you know, when you want to push the boundary and go to fullerenes, for example, C5 is an important player. But C5 gives curvature, it gives optical property somehow, changes once you have a different curvature for the nanoparticle. So the 5-member rings plays a key role, as I will show you later. The one on the right also shows another type of pathway. So here you have a 5-member in the center. But here, one more thing can happen is that you can have somehow a different pathway, and now the 5-member rings is on the outside. So you can have addition from the gas phase, you can have rearrangement also, and this is becoming complex at the minimum. same line. Now I have, the bigger the molecule, the more pathways you have. So this is something also that we've been looking at. Okay, so, but all this modeling has always been somehow supported by experimental work. So I think there is a great point in having always synergy between modeling and experiment. And here I just want to show you some experimental work I got it. I mean, I just wanted to report actually something that I also used to read many years ago. And I like that because this is telling you something different. So far, thermochemistry tell you there are stabilomers. People think about pathways that can lead to those stabilomers, but the picture is way more complicated than that. And so this is a work done by Hohmann many years ago. And in Germany, and what he did, he was able to sample for an acetylene and oxygen flame was a low-pressure flame with the CO1, and he used molecular beam high-resolution mass spectrometry to do that. And the message here is that he could measure different compounds in his system. And what you see here is the number of carbon in the molecules and the number of hydrogen once you have even carbon and odd carbon, okay? And the lines are the stabilomers here. So those guys on the left. So what this is telling you, this is the message, is that the chemistry is not stabilomers only, but it's way more complicated than that. And so, I'm just increasing the complexity of the picture. So this is clearly showing that now you form different compounds that are not the one only based on those, but you need to think about something different for that. So the next step at this point is that I think my purpose for this talk is not only to tell you again what is people have done or they're doing, but also tell you what the problems are. So pathways are still not well defined. There are experimental data that come out constantly, and still the molecules and the mechanism that we have still don't do a great job. So here I just reported, and I have no preference, I just want to be, I took, although there is this beautiful study that we have, although people are publishing mechanism, and although there is a lot of quantum chemistry going on, we still are far, especially for the aromatic growth. So if I have to identify, areas of need, as you guys are moving maybe from the PhD or the postdocs also to think about combustion avenues within relation to chemistry, formation of aromatics is a big deal here. And so I'm just comparing, this is some simulation that we did with different mechanisms that we found in the literature. And we wanted to look at the mole fraction for, this was a pre-mixed benzene flames that I found experimentally. Not many people measure pHs, so it's not easy to find experimental data. This was one of the Italian groups that measured the benzene flame with the CO 0.77 and 1 atmosphere. And they were able to report, I think it was with the CG, gas chromatography, basically the concentration profile of naphthalene and cyclopentane. So naphthalene is 2 6-member rings, cyclopentane is the 5-member rings. And the only point I want to make here, that it doesn't matter who the authors are, but the point is that we still don't know. We still don't have a way to predict this very well. Okay? So there is an error. There is an error that sometimes, if you see, will end up with a shift in the peak. So you don't even know at what distance you're forming this compound, of course, in the quantity, the amount that you have. So what's the lesson we learned? So pH precursor chemistry, it's a complex. I think is an important point to highlight, and is very sensitive to the main flame chemistry. I show you that you go from the fuel to those small hydrocarbons, but they are the precursors. If you think about acetylene, propargyl, they go to benzene. Benzene will go to a bigger pHs. And so main flame chemistry, local temperature, the fuel structures, and the composition are all factors that play a role in the definition of this pH chemistry. And possibly a large number of pathways to pHs have not yet been considered. So, and again, this is my opinion. But I think we still miss a lot, not only in terms of being accurate with the rates, but even in terms of thinking the pathways that can lead to those compounds. So if I have to highlight the needs that I see, especially for this field, I think there is a need to resolve the uncertainty that there are in chemical composition of these initial pH that we formed. So a knowledge of the chemical pathways, better knowledge. And so one of the issues that you have seen in this, the way people have developed mechanism is that somehow you have an idea of where you want to go, okay? And so there is a bias there. And so people can only think about what they know somehow. But ideally, you will want a system in which the fuel will evolve and follow their, wherever they want to go. And so that could lead to the formation of different compounds. The accuracy of the rates is also interesting to determine it. And so there is a refinement, overall, a refinement of the kinetic models, especially for the pH. Okay. So I would like now to transition to the nanoparticle formation and start talking a little bit about how can we go now from aromatics, so to all the way to those bigger particles that you have seen. So I was not timing this correctly, so I was thinking we need to take a break now, but let's keep going a little bit more, and then we'll take a break. Okay, so you are in this gas phase now, okay? And so the question is, why should you form this condensed material? Why do you think that this gas phase really wants to form these particles in solid? And so this is a great graph that was reported by Professor Hai Wang in one of the plenary that they gave to the symposium in 2011. And this is showing you, just to simplify here the system, is that if you have a propane and you look at the state, so stay with me with the state. So if you look at the formation of benzene, this is acetylene, and then you see just the formation, okay? The benzene, naphthalene, and pyrene. What you can compute the enthalpy and the entropy for all those states, okay? Then overall, you will get a delta G. The delta G is how spontaneous this process is going to be. That overall is going to be negative. Okay? There is always a balance between the enthalpy and the entropy of the process. And of course, the condition which the combustion is happening will change the relative importance. But overall, you can look at this as delta G negative. So if I have a propane C3H8, and I look at the delta G for the states, so benzene, then I'll see that. The point I want to make about this is that this is the beginning of the story. Because if you look only at the states, then you have this type of graph. But what happened with a system like the one I showed you before, a valley, okay? So what if, in order to go from, let's say, species A or species B, A and B, so here, for example, now I have a huge barrier. Even if benzene and naphthalene, if you look at the states, they are, very favorable, maybe there is a barrier and I can never get there. So the point is that, what about the kinetic property depends on the free energy of the system, right? And so the thermodynamic, the point is that we cannot just look at the states, but we need to have a more holistic view of the system. And so the approach that I want to show you that we took was to look at the system, see how they evolve, but not only the state, try to look also at the dynamic. So if you remember the picture I showed you before with the valleys, and try to see how they move from one valley to another with some atomistic simulations. So only thermodynamics is not going to be the answer here. And so let's take a look at what happens in combustion first, and then see how we can solve with some modeling approach. There's been a lot of interest in nanoparticles and soot, and there are huge and wonderful reviews that have been published over the years. Here I listed some of those, together with the roundtable discussions, so many years ago. So this is an opportunity if you're interested in looking at some of those. But this is an historical plot, and I guess I have to say this is one of the first I ever seen with my PhD. And this is a historical plot for me, and it was done by Wagner in the soot roundtable discussion in 1987. The point here that I want to make is that he plotted the the mole fraction of hydrogen versus the log of the molecular weight, if you want here. And so this shows how they change over in a flame. And so you can have, for simple compound, those values with the molecular weight and the H, and they are all here. You remember the gas phase? Then eventually you form those pH that are now here, and then down here with the higher molecular weight is a soot. Okay. And so the message here is that soot is not really coming directly from pHs. So there is no straight pathway from here to this guy. Okay? But something more complex is happening between the pH and the soot that can be seen experimentally. And so what I'm going to highlight for this the next slide is the formation of what they see as nanoparticles. New technique have allowed the detection of this material. So initially, many years ago, this was not possible. And so in between the soot formation, the big aggregate, and the gas phase species, there is an entire world that is the nanoparticle material. Now, nanoparticles are really interesting because as we care about the health effect, those are the ones responsible for the majority of the health effect. So from a perspective, just the interaction with the biological system, if you think about big nanoparticles, big particle like soot, and you think about breathing those particles, they get stopped, whether it's in the nose or in the throat. But the nanoparticle, there is no way they can be stopped in the body. And so people have seen and detected those inside the body. So somehow we deal with that, and they accumulate in the body. So if the final goal is to look at the assessment of those material byproduct formed during combustion, nanoparticles are keys for that reason, but they are key to if you want to develop a model for soot. So the existence of nanoparticles, the first time were observed were Wurzburg in 1973, and is a molecular beam sampling. They start looking at small nanoparticles. Then there is all the work of the Italian group led by D'Alessio many years ago, and they use optical technique. They look at absorption, at the extinction, and somehow they were able to identify the presence of these nanoparticles. They were transparent in the visible, so we'll see. They don't absorb in the visible. We'll talk about that. And then additional evidence came over the years with different techniques. So there was the work done by Hai Wang and many, many others, great research here. I just listed, DMA was one, small angle scattering measurement, photoionization mass spectrometry experiment, so something where also you heard today. But there was also a little bit of limited information about the chemistry here. So talking about nanoparticles, I think one of the needs that we have in this area that is not clear is what's the chemical composition of this particle. So this is some of the work that just highlight the information that we have. So this is, again, part of the Italian group, and what you see here is the laser-induced fluorescence, and the absorption of the fluorescence here. What they show between the two ethylene flames, a different CO ratio, is that there must be two rings aromatic connected by aliphatic, so by those experiments, basically. So we start getting some information about the chemistry that we can have, but still it's very limited. More work has been done also with, for example, the DMA. Okay, they measured the particle size distribution, and this is another flame that was done by the group working with Hai Wang. And the idea is that here, as you move in the premixed flames, you have distribution of the particle, the size of the nanoparticle. That initially are they are a single distribution here, but as you evolve in time and the distance, they become bimodal. Okay, what that means to you, if you're thinking about the modeling, is that the transition. So what they define nucleation, how I go from my gas phase species that I form, my pHs, to the nanoparticles, if you analyze this graph, is that is a second order kinetics, okay? And what that means that there must be some kind of dimerization. So it has to be, the rate needs to depend on two factors, if you want, for the concentration of the two species, and those are dimers. So even if we don't have a direct number for the rates, experiments have helped us to create those pathways. The first order nucleation instead gives just distribution that are unimodal. Since we see bimodality, that means that there was some kind of dimerization. So some people look at the chemistry, and it seems there are few aromatics connected with aliphatic bond. Other people are looking at maybe dimerization. More experimental work on this transition was the mass spectrum of fragments from the photoionization of soot. And this is the work done by Grotter in 2007. And this is for an acetylene oxygen flame. And the point is that those flames show some periodicity with the frequency around 500. And there are more details in this paper. And so these features of these peaks basically suggest that pHs, they stuck. So they form, once you form those initial pH, they transition, but they form some dimers. They stack on each other. Okay, so this is all some great experimental work that we have been leveraged to start thinking about our modeling. So over the years, the particles, the chemistry of the particles and the modeling that has changed. And initially, the soot or the nanoparticle were defined as the mass accumulated in pHs above a certain size. Okay, and so that was a pure chemical growth. So once I have those my pHs, they start reacting with each other and they form bigger structures. And this type of definition was used in the past for a long time, but for some condition, it was not working very well. Later, they found that pH sticks to each other. So in addition to chemistry, now there is some physical interaction that's contributing to the growth. And so they came up with the new models. And actually, it's very tricky, and it still is very tricky, because all the pH, the practical measure of dimers, once you form dimers, you will form solid particle. So somehow, when you look at the modeling, you form dimers, and then at that point, you define as a particle. Okay? So there was no accurate description, but just a mathematical approach for that. So dimerization, so I have those pHs that get together, was really important. And here, there is a lot of work that's been done also with, again, ab initio simulation to look at the tendency of those pH to stay together. As a function, what you see is the binding energy as a function of the number of carbons. And the top shows, the binding energy increasing as you increase the size because they attract to each other more. But the bottom shows that, the concentration in flames, those compounds, goes down. So the bigger the pH, the higher the concentration. So just from a probability standpoint, those pHs, if you have to get to circumcoronin to start having a significant binding, then the concentration is too low to have a meaning for the growth of soot. So a lot of data that's been produced from theoretically and also experimental data, and there is no final answer to that. So what I can summarize at this point for this brief review is that really, once you have those pHs that you really form, there are two classes of compounds that they are detected in the combustion system, and I'm mainly talking about the flame here as I show you. And so there are nanoparticles with size in the range of 1 to 5 nanometers, and then there are more soot-like particles that go from 10 to 100 nanometers. The chemistry and the type of reaction is completely different. And what we have right now, there are chemical and spectroscopic analysis that give indication of the nature of those pH or polymer-like chemistry that is going on. But we need more quantification of this process. So we have, in principle, a physical growth for some evidence in which the pH bind to each other, and then you have a chemical growth in which they form a bond and they keep growing. In this picture, soot, as we move forward, so there is a lot of limited information about the nanoparticles, but there are comprehensive models that also try to go all the way to soot. And so the idea is that the soot is the coagulation of those 1 through 5 nanometers particles, and that together with the addition of gas phase species, they lead to the formation of soot, so condensed ring aromatics. And the main approach that we have in the literature are basically use of mathematical solutions, and there are two main field, if you want, two main areas that combine the gas phase with aromatic growth. It's the method of moments, and maybe some of you heard about that. Really starts with Franklin again, and so the way is to solve your chemistry together with the equation that define the system, as the particle dynamic is described as the moments of the particle size distribution. And so you can get information about the volume fraction, the particle size, all mathematical approach. The second one that has been followed, I will say, by more people lately, has been the sectional method. And so basically the idea is that you have an ensemble of aromatics, and you divide into classes of different molecular weights, and then you treat each class as like a gas phase. And so this has led a lot of interesting attempt to develop the soot. So let me summarize for a second what I've said. So we started with the chemistry of the fuel. The fuel are complicated. My goal is to grow in size, to go from the fuel to first small hydrocarbons, and then somehow you have the formation of this aromatic. What I see as a first need and unknown is really the chemistry of pHs at this point. And so many things are not clear, and I show you an example with that comparison between experimental modeling. And in addition, you're not clear on those gas phase precursors, and still what happened next is still unknown. So now you have precursors that are not right or not completely matched with experimental, and now you build a molecule for particle dynamics on top. And so this has advantages, because sometimes people are only interested, in the soot formation, and sometimes there are some parameters that you can adjust, and people are attempting different approaches to do that. But the vision right now is to use a mathematical approach, like the method of moments, that is mathematical resolution, to grow in size. So what I would like, since I gave you this as a really review of what's happening right now in the literature, I want to tell you what has been our contribution. And since at this point, maybe I need to dig a little bit into these molecular simulations that were out. Maybe we can stop for 5 more minutes, and then we'll go to molecular dynamic simulations. Okay? And if you have any questions, let me know. 5 minutes break. Yeah, go ahead, Anger.
Replay.
Yeah, well, I'm not sure if it's actually a question, but I've been doing this sooting flame modeling studies. What our Coust mechanism, we have Aramco-based Coust sooting, all the pH mechanism built in. What we are bragging about to the rest of the community is that we have all these higher pHs, all the way up to chronin, and with some huge uncertainties in terms of accurate dimerization rate constants. Nevertheless, the general finding is that they contribute a lot to the soot formation. So actually, in terms of overall soot volume prediction, it makes a huge difference.
Yes.
And there always a problem has been under prediction than over prediction. So the more soot you produce, the better. Well, whether it's accurate or not is a question. Mm-hmm. So that kind of contrasts your comments about those role of higher pHs. Would you like to respond to that?
First of all, the pHs, so the pH formation, so there are some ability, some mechanisms that can do a better job or a worse job, depending also on the conditions that you have. What I was talking here is, first of all, on the transition, so the inception, because I think what's not clear is how do you go from, for example, a pyrene all the way to those dimerization you were talking about, and eventually soot. The second, and this is the first unknown. The second, maybe I think that can answer your comment, is that yes, we are pretty good right now with the soot modeling to look at the soot fraction. So the FV that you have in soot modeling is usually matched not too badly, right? And this comes from the fact that you have also an adjustment parameter that is the active site on the molecule that people sometimes twist a little bit. My point here is that what we really care about, and at least even if we want to talk about the health effect, is that the transition. So I care about find a way to develop nanoparticles in our system. And so not too much the soot that you were talking about, but more the nanoparticle. And for those, understanding how the pHs grow, it's really fundamental. So part of your answer is yes, you're correct. Soot volume fraction, final number, yes, you're right. We're doing a good job with the current models for that, because they are not influenced as much from the gas phase chemistry of the pyrene. Because there are other ways to tweak the result in the end, I mean, to adjust. But the transition from the second part, the nanoparticle, is a little bit more challenging. Yeah.
Way in the back, okay. Hang tight.
Professor, I have a couple of questions and comments also. One of the things is what we measure and what matters when we talk about engines is actually at the end of the turbine, or in power gen cases at stack. And that's what comes out of the, and that's what matters to the population. Now, and there are many ways where you can actually look into primary particulate matter, secondary particulate matter. And presently we are looking into soot, which is essentially what is formed in combustor. But when it goes through stages in turbine, stages in different parts of the power plant, and comes out of a stack, it is a very different thing actually. Now my question is, are we there yet, or can we ever predict real PM, which matters actually?
When you say real PM, you mean what do you want to predict?
Yes, like PM 2.5 is not at the end of combustor that matters to us. It's what comes out of the stack or the engine in aviation cases. So is there any way?
So that's exactly also what happened with an engine, right? You in your engine, you are burning stuff, but then your byproduct goes through the tailpipe, in which the chemistry is changing. So, and of course, what comes out of an engine sometimes is different. It's not necessarily everything from the engine, but it undergoes some different chemistry. At the tailpipe, the temperature is lower. You can have coagulation that you will not have before. So, to your point, to your question is that there is more chemistry than just the fuel combustion that we're talking here.
Exactly.
And, but this is the first step. Because if somehow you can predict exactly what comes out of the engine, maybe before it goes to tailpipe, then you have more information to control that in the tailpipe. So I think trying to understand that as a first step of what's happening, it's really important here. And I totally agree with you that what comes after is, could be different depending on the environment that the particles or the gas phase species meet during their evolution. This will be my last part of this presentation for this afternoon. So now I get to more what we do. So the purpose, again, was to tell you a little bit what people have been doing, what are the current trends, what I believe is like unknown and requires effort. But also, as I was mentioning at the beginning, I think this is an opportunity for a week for you to get familiar with other people are doing and maybe use different technique. One of the flavor of combustion is that really can be approached in different ways. Not only if you distinguish between experimental and theoretical approach, but even within the theoretical approach, you can go from more empirical equations, what you've seen, CFD simulations, kinetics, all the way down to atoms moving. So I gave you a framework. There are a lot of steps involved in the fuel. So I need the fuel, I need the gas phase, then I need somehow to transition from those aromatics to my particles. And so that is really important, especially if your target is to understand the formation of those nanoparticles. Not too much the soot, but let's talk about those nanoparticles for a moment. So what have we done? Sorry. What we are interested in is to develop a model for the formation of nanoparticles. because mainly of the health effect, I have to say. That was the driving force. But we want to provide some information about the physics and the chemistry. So I was showing some experimental data that provide some information. We wanted to have a modeling approach for that. The reason is that all those parameters, whether it is the shape, the mass, the chemical composition, they all are important once you talk about environmental consequence of this material. And so what we use as a tool is what a molecular dynamics computational approach. Okay, so let's go to one of the cartoons that I usually like to present. That was initially from Bocorn in 1994. And then somehow I readapted, introducing part of the work that we do. So first of all, the reason why I have this cartoon, it shows a lot of information about some of the processes that I mentioned before. And so we go from, if I find my cursor here, sorry. So here, you start at the beginning with your fuel and oxygen. Then you start with the gas phase formation, remember? And those are compounds that eventually go to the growth of aromatics here. So we talk about 1 ring, 2 rings, and everything that is available right now with the mechanism. Then eventually, you form nanoparticles. Somehow, there is a transition regime that goes from the pH to nanoparticles that is called inception. So somehow, those nanoparticles are formed. And then once you form that, as I was mentioning before, you form those, then they start to coagulate with each other. You will see addition of gas phase species, and then eventually they grow up to the end of formation of soot that is more fractal. Okay. One of the interests that we have is really in this region, transition region, and try to find a way to define this step. Now, so where are we? Where do we stand? So the models that are now available in the literature for soot formation, they use pyrene, that is this guy here, dimerization of pyrene as a step to become a nanoparticle. So what they define as inception is basically this pyrene, you form pyrene in the gas phase, and then there is a tendency of this pyrene in, for example, a flame condition here to form a dimer. Once you have the dimer, then you keep growing. And so this transition is defined as dimerization of pyrene. Now, so irreversible dimerization also, pyrene, is the initial step for nucleation in all the soot models available. The recent works show that it's very unlikely, okay? And there are many experimental work and computational work on this topic, but nevertheless, without an alternative, people who are developing soot modeling still use this as an inception. So that's one of the things that we wanted to address. So, and the second part I want to show you is that the nucleation, the soot nucleation, and the mass growth are still phenomenological approach. So when we talk about people who have soot modeling, those two steps that comes a little later, the soot nucleation and the mass growth here are still phenomenological, okay? So there is a lot of room for improvement here. And so one of the things that, again, we wanted to see was to look at this transition using a different approach. So something that was not just, you know, pyrene plus pyrene becomes a dimer, but start looking at really what's happened to the system a little bit. So if I look at this cartoon again, the idea was to try to enlarge, blow up this section. So instead of having in a mathematical form my A plus AI plus AJ becomes a dimer, try to follow the evolution of those material with this level of details. So the first problem that you see here is that there is a huge time scale involved in here. So I'm going from phenomena that happen on the time scale of 10 milliseconds here, you know, for the formation of this gas phase species, and then to my need of studying the formation of those nanoparticles at this level of details. And then at that point, you have all those possible reactions I showed you before, including rearrangement, and they happen on another time scale. So that was a big problem. So let me tell you how we have done this slowly. We're still doing that. So the first thing that we want to address in this big picture is, can we say something about this dimerization? So dimerization seems to be important to everybody. Let's take a look and see if we can provide novel information. So there were two main growth mechanism. I show you some evidence and experimental evidence and some theoretical evidence in which there is a physical clustering of pH that you form, like pyrene, they form a dimer, and they eventually keep growing and becomes nanoparticles. And then there is a second way of growing that is forming actually a bond. So the chemical linking of pHs. Those are two different things, so chemistry and physics together. And the experiments and the theory are still uncertain which one is the most dominant things. And again, the soot model currently uses dimerization as a step there. So our approach is, we wanted to look at this. And so we want to look at the free energy. So the way we have done this is, first of all, look at a molecular dynamic simulation. And I don't know how many of you are familiar with this, but molecular dynamic simulation is an atomistic tool, and basically is somehow to solve a Newton equation for your system. So think about two molecules, and you draw the molecules, so you do know the mass. You need to have some information about how the atoms interact with each other, and this is actually a force field, the potential for molecular dynamic simulation people. And then what you compute is the evolution, the dynamic of the system. Okay, and and then you can compute a lot of other properties that are of interest. So what we have done over the years is look at, for example, as a first question for the dimerization was the free energy. So free energy tells you how likely is that the two pyrene will form a dimer. Okay, and one of the problems with molecular dynamic simulation, on the limitation of the problem, is the time scale. Molecular dynamic simulation can only go up to maybe 1 picosecond, depending on the system, the condition, as a time scale. Some of those processes happen at a very longer time scale. So we have been using a lot of tricks, computational trick, and so we are a molecular dynamic simulation and combined with, I'll show you what it is, with advanced sampling technique, so it's called metadynamic, to look at the formation of the dimer. Again, the question is, I have two pyrene, will they form a dimer, yes or not? We look at the free energy, and the free energy is interesting, as I was showing you before, is because it tells you something about not only the energy of the system, but also the entropic contribution. So usually people look at the delta H only. There is entropy that plays a role, especially when you are at a higher temperature. So plus, the free energy accounts for configurational effects, morphology, okay? So let me show you if this works today. I don't know if it's working on my thing or yours. Okay, so here maybe. Okay, so do you remember that we need to, is it working? No, it's not working. Ouch. Okay, so I don't know why it's not working, but not working. Okay, so this is one of the valleys I was showing you before. Remember that in order for you to understand, to study the dynamic of the system, you really need to look at the states that you want to go through, but also at the height of the barrier. You need to be able to explore the landscape. Otherwise, you only have the states, and then if there is a huge barrier, you're not going anywhere. Okay, somehow. And so this technique and this movie that is not working, is supposed to work, shows that what you do is a mathematical trick in which you still want to go from one valley to the other valley, and what you do to your system is to add a potential. So you help the system to overpass those barriers, and somehow what you do, you make sure that the system becomes, explore the whole landscape. Okay, so molecular dynamic simulation combined with this technique, sorry, you can see the movie, and so we started first thing, the free energy. Okay, so let me show you some of those results, at least they are working. So what I'm showing you here is the delta, so the free energy on the y-axis, and the molecular dynamic simulation on, this is the distance. What I mean by distance is the distance between the center of mass of two molecules. What this is telling you, and this is a 1000 Kelvin, right? It's telling you if you look at how the atoms behave in your system, so you create a box in which you have two of those molecules, you set the temperature, and now you want to see how they evolve. So this is telling you that if they are far apart, they are monomers, right? They are far away. And then as the distance decreases, you go in a well here. And so at 1000 Kelvin, only something that is as big as a circumcoronine will have a dip. So you will see the formation of a stable dimer only if you go at this size of pH, while compounds like pyrene, basically, they have no minimum in this scenario. So this kind of simulation basically reported that in order for you to coagulate to form a diaper, you need a big size of pHs. At this temperature, small pHs do not coagulate. And so even Ovalin, that is this type of pH formed this green curve, forms a dimer, but then you have to look at the energy to escape this valley versus the thermal energy at that specific temperature. So in conclusion, for this graph, the free energy is telling you that, yes, if you have a circumcoronene at 1,000 Kelvin, you will form a dimer. Pyrene will not form a dimer. Now, the second question is, how much of this pH do you have in combustion? And the answer is very, very, very low concentration. So pyrene as a dimer is not physical as a process to grow structures. So we were looking for alternatives. Using molecular dynamic simulation, we did something similar. So now we run some simulations again, in which I have my system, the pyrene. And by the way, this was a lower temperature. And what you see here is that I'm still looking at the free energy. And this is the monomers, so separated. And now, if I add some chains to my pyrene, so if I have ethyl pyrene here or vinyl, the pyrene here, then the free energy is changing. And so the message here is that if somehow I'm changing the configuration of my, the chemistry of my pHs, so if I have an aliphatic chain attached, for example, then the dimer will form. And the reason why this happens is that once they get together, they have a lot of energy, those compounds, but if you have a degree of freedom, for example, in the chain attached, then you are able to stabilize the dimer because part of the energy is taken by, for example, the vibration, the rotation of the chain. So the message here is that using those very atomistic simulations, we we identified molecules that actually are not the pyrene, pure pyrene, but if they have attached a chain, could actually coagulate. And definitely in the flame, you can find more of these compounds as compared to the bigger pH that you saw before. So, yeah, this is telling you that this guy, and the other question is that while this tooth guy, although they have the same length of the chain, they have different free energy here. And the reason is because this is a double bond, so it does not move much, it's very rigid, compared with the single chain that can rotate a lot. So the one that easily rotates has more steric hindrance, if you want. And so it's more, the flexibility of this chain also plays a role. So the main result from this, we look at this inception, we try to look at the dimerization, and the idea is that using these molecular dynamic simulations, we are looking at how atoms evolve over time and the free energy. So the goal is to provide the people who are developing soot modeling with some information that can be used or plugged in to justify some of the assumptions. And so using those free energy methods, basically, we were able to enhance, if you want, the clustering behavior. And so we accounted for the entropic contribution that were not taken into account before, and also understand that the dimers of pyrene is unlikely, does not happen at flame temperature, so not even at 1,000 Kelvin they will form a dimer. But other compounds that maybe have not been overlooked, have been overlooked in the past, just because you add some chain, it could play a role into the dimerization. And I'm talking about the physical growth of these nanomaterials. Okay, so, but the next step that we wanted to do was also the chemistry. Remember, there are two different pathways. So we are looking at the physical growth, and so what information can we get versus the chemistry. Now, for the chemistry, we were interested in pHs. You remember I told you that one of the chemistry of the aromatics that we don't know is really a problem for this point. So the chemical growth was, I have this, for example, my aromatic, and then I have some steps that happens. Is there a way I could see what happened to the system without biasing that, strongly biasing that? And so we came up with some ideas on how to use molecular simulation to study this process. So this is a code that we started a few years ago. We are now in a new version with the a lot of implementation. But let me tell you a little bit what is the basic things here. So we look at molecular Monte Carlo simulation, so another atomistic approach, and we take our molecules. So let's say that you are a benzene, you form the first aromatic. Then you remember the issue is that how do I grow in pHs? Then with the Monte Carlo, we take our system and we place in high temperature regimes, so high temperature, and then we define some of the components that are around. So you know the gas phase, we talked about this a little bit before. And so at this point, based on probability or the rates of this species, how likely is that, for example, I have this acetylene or this acetylene will react with this aromatic, we let the system evolve. And so we take inputs from the gas phase and we try to study the formation of those pH systems. So what the system does, what the code does, is basically simulates a trajectory that describes a time history of the reaction of the system. So if I have my benzene in a flame, how does it grow and why it grows that way? So the first problem that we have with this is that as an input, you need some reaction, so you need to know what's happened to the system. And the second thing is that how you define the chemistry, because if you have a benzene plus acetylene, it's easy. You know what you're adding. But if you want to grow, basically, eventually you ended up with a blob that is not well defined. So one of the key of this program that we have is to look at the reaction side. So we don't look at the overall entity of the system, but rather to, I have some site on an aromatic island here. What's the tendency, what's the probability to react with the aliphatic things, okay? So this is a lot of, and then we define, different species that can be added. You can have rearrangement, you can have hydrogen, but the idea is that let's look at how they evolve in a flame. And hopefully this will work because so I want to give you just a cartoon of what we are doing right now to study these processes. Again, we're looking really at a very fundamental approach here. So this is just a cartoon of a flame. Think about a candle, and the blue part in the candle is the high temperature regimes. When you get the yellow stuff, is basically you're forming those byproducts. So you're forming nanoparticles, you're forming soot eventually. So what happened to our system here? Let's see if it works. So if I take one of my initial pH that I was showing you before, and I place in environment, and we'll say, I have this amount of acetylene, this temperature, and those are my conditions. Our system hopefully will work. The code that we have does something that looks like this. So we develop, or also still developing this code that allow you to look at really what's happening at the molecules. So once I form my aromatics, initial aromatic, instead of transitioning to the particles, just as say pyrene, and then this is a soot nucleus, I want to follow exactly what happens to my molecules. So here you're looking at small aromatics that from the gas phase placed in high temperature regimes with acetylene hydrogen around it and some other pHs. And basically the code, this is a SNAPS code, what it does is grow structures. Deciding without, so the only bias that we have in this code is the probability that the reaction can happen. But we don't say anything about, if you have benzene, you have to go to this product. The system is evolving by itself. And so we have been able to follow the growth of some of this material. We're still developing this thing. But the point is that now it's no longer a mathematical approach, but becomes more quantified with the molecular distribution. So once I form those nanoparticles that now are growing by chemistry, I can tell you, what's the hydrogen carbon ratio. I can tell you what's the mass. I can tell you, what's, for example, the density. What are the number of radicals? Those are all properties that if you want to develop an over-comprehensive model for soot, you can translate into some kind of dependency of or rate of based on the characteristic of these nanoparticles. So this is what we are doing. We like atomistic simulation. So but again, I really think that it's very important always to try to always combine with experiment. So I want to just briefly talk about collaboration that we had over the years with the group at Sandia. And so what they they do in terms of experiment is measuring some of the byproducts of combustions. So we have some data here from an acetylene counterflow flame. So this was an acetylene oxygen flames. Those are some details if you're interested in. And so what you see here is the fuel. This is the soot zone. This is the stagnation. This is the oxidizer. There's some more information. So what we did is to look at snaps that I just described to you and see, once I have some aromatics in this configuration, what kind of system do I form? So let's say that I have my benzene. How do I grow to pHs, bigger compounds? So from the perspective of the experimental side, what the group does at Sandia is basically use an aerosol mass spectrometry with vacuum ultraviolet single photon ionization. So big words here. But the idea is that they sample in flames. So the flames will be the counterflow flames that I was talking about. And then they collect the material and they direct on a lens. And then you look at the fragments that are on the material. And so this has been well developed over the years. And what kind of data do they get? They get the mass spectra. So if they probe at a certain height in the flame, what they come out with is basically the mass spectra at that height. So you have information about mass information about the compounds that are at that level. So for this specific flame, as I told you, we had experimental data at different heights from the group at Sandia. We ran our SNAPS simulations because if we were trying to these are the type of results that we got. So let me say this first. So this is acetylene oxygen counterflow flame. This is the experimental data that they got for us. So the ion signal telling you, what are the molecular masses present at the specific height in the system. And those are some of the results that we got from our SNAPS simulations. So the point is that using this SNAP simulation, now we are able to identify or grow material that if you think about a simple, like a Haka mechanism in which you go, or chemical approach, for the pH growth that we're talking a few hours, an hour before, you will not be able. So if you run like a mechanism that is a gas phase mechanism right now, to the growth of those aromatics here, you will not see the same amount of peaks that you will see with the SNAPS code. The way the SNAPS work is that it grows materials, and so you can end up in a pathway that you didn't think before, because the system will decide what reaction to happen. And so let's say the beauty at this point is that we're really excited about. Using this atomistic simulation, we try to get more information about the chemistry of those materials. Once I have that information, then I can slowly grow into my bigger systems. But this is one of the results. And I don't know if you can see, because I don't know. So what I want to say that is for specific this flame that I just show you here, we ran SNAPS simulation, and for the mass of 202, that is pyrene, we came up with this kind of compound. So our simulation, and for the case, just to give you an idea, we ran 10,000 trajectories to see what happened to our pH. We found out that 38% was this compound, and then pyrene was only 12%. So there is a lot of compounds that are formed that are not accounted in the current mechanism, if you want that. And so pyrene is not the highest mole fraction in these cases, but compounds with 5-member rings were also very interesting for the system. From the experimental point of view, this was validated with the photo energy that was computed. So here I'm reporting for the mass 202, the pyrene. So if in the flame there was a lot of pyrene, so only pyrene, that will be in the signal gotten from the experimental point of view. But in the flame, what they were able to sample was 9.5 millimeters, something that was different from that. And so what this told them, basically, that these are two different heights to show you that the composition is not pure pyrene. Okay, so if you want is an indirect validation of SNAPS, SNAPS is telling you pyrene is not the highest. There are a bunch of other compounds for the same mass, isomers, that are present in higher concentration. The photoionization here is telling you we agree somehow, because otherwise our signal would have been this guy, but there is something more that is contributing. So this is a very interesting region and is very high, very difficult to sample. There are efforts going on, try to come up with experimental validation of this region or experimental data. But things are happening very fast, is highly reactive, temperature is very high also, and so the data are not as many as we would like. So this is just say what I was saying. Okay. Now, one more thing that we have done on this. So still using snaps, using these atomistic simulations. We used some of the oxygen chemistry that we took from ab initio simulation. So we thought about what could be a pathway for oxygen to be added to these aromatics. And so we came up with some possible idea with the oxygen content. And so in case you have an aromatic with any kind of attachment here, doesn't matter. But if you add OH, then you form you can eventually, there is a case in which you can close the system here and form a furane type molecules. And so here is just an example of the energy, the transition state, and the quantum chemistry that we did. But the point is that now that we had this idea of some initial preliminary result on the oxygen chemistry that we want to implement into SNAPs. We did that and for simple cases, and now we can have a case in which oxygen is formed and is added to the pH. So you can have the formation of ethers, esters, but also furane-type materials. And so that led us to a work that here I'm just summarizing, again with the group at Sandia, in which we were able to reproduce some of the peaks, again, the mass spectrum that they saw. So here is the flame, and these are different heights. And what you see is in red is the peaks of pHs that they have oxygen on it. Our simulations with the SNAPs show that the mass spectra could be reproduced, and we were able also to track some of the oxygenated species on the pHs. This one on the right is showing you how this, the type of bond evolves over time. For example, here I have the distance from the burner for this flame, and this tells you that the type of bond CO, double O, or COC, or COH evolve over time. Okay, so those are interesting data, and the more we have on this stage, the happier we get. So at this point, we have an ability to simulate nanoparticles, or transition from those small aromatics all the way to bigger clusters, big aromatic nanoparticles. And we are looking always for more ways to validate the mechanism. So this was an interesting paper because for the first time what we saw, if I go back here for a second, is that, and actually maybe here is better, this pathway could be important in hydrocarbon combustion. And so even if you start from a fuel that somehow does not have oxygen, so there was an ethylene oxygen flames, eventually you can run into condition in which the oxygen is embedded in the ring. And so that leads to the formation of furane type compounds that are very carcinogenic. So the oxygen chemistry will be our next step to look at. And so the introduction of the oxygen chemistry into the aromatics, the pH growth. So if you remember the graph I showed you before, in which there was a simple two rectangles in which I say, okay, fuel becomes CO, CO2, and hydrocarbons, then the scenario becomes way more complex. So not only we have to form pyrene, but the growth to pH is more complex. Oxygen needs to be included, and eventually we need to talk about the transition to nanoparticles. Okay, so this was just a cartoon showing that the fuel also dictated the number of macromolecules that we form. So think about if you're running a benzene flame or versus an aliphatic flames of ethylene. If you look at the pathway that I showed you before, if you have an ethylene flames, what you need to do is to form benzene eventually. So you first break down, and then you form benzene, right? And then you grow to aromatic, and you follow the growth. So the gas phase at the environment that the ethylene fuel will undergo is completely different than if you start again from a benzene, because at this point you have a benzene from the beginning, and so the pathways of growth are different. So this was a cartoon in which the fuel was an aliphatic, and this was a benzene was the fuel. They have the same mass, but what you can see is that the shape is very different. So this is not just a particle of, like, say, 200 carbon atoms. This is a particle we can say something about the chemical composition, but also we can say something about the shape. And so if you remember, the formation of five-member rings gives some curvature, and have a tool that can distinguish or can somehow give you information about the curvature and means optical properties of this material. So if this fuel gives molecules with more curvature, and I go into a kind of a broader view approach here, then, if you're concerned, for example, with the environmental effect and interaction with the light, then the optical property of this is going to be very different from this one. And so what you could do, for example, is a source assignment to say what fuel produce more curvature, compounds with curvature, for example, that have this type of optical properties. So there's a lot of questions that you can answer once you start having a structure of the molecules. This is an interesting, there is still a lot of work that needs to be done if you really want to get to the fundamentals of the processes. And so our goal has been really to provide some insight that can be used for developing this, a better soot modeling. And chemical composition is one of the critical factors in this growth. So we need to know something about, especially this transition region, where things happen very quickly. So in terms of needs that I see for this, and maybe people again interested in this field further, is that there are uncertainty in the chemical composition of the pHs. We talked about this. We need to know something about the chemical pathways, the rates, the kinetic models, but also especially, I would say, we need experimental data on the chemical composition of these transition regimes. So something is in the literature, and just I have an example here. This is something about the hydrogen-carbon ratio experimentally that was reported by, I think it was the Italian group, but like a few years ago. So what they did is basically look at the hydrogen-carbon ratio, and those are different flames, resident premixed laminar flames. And so what different flames of methane, ethylene, and benzene in one atmosphere. And what they saw with the FTIR was the amount of CH2 groups in methane flames is a higher hydrogen-carbon ratio. Okay, and instead the benzene has a lower hydrogen-carbon ratio. Okay, so those are indirect measurements. They tell you something about aromaticity. I was showing you that, growing snaps, for example, you get different structures. Something that is more aromatic means also, a different hydrogen-carbon ratio than you can have in aliphatic flames. So those are indirect validation for us, but they really tells you that things don't grow. They grow depending on the fuel and the environment that you see. So we cannot just have, one overall description, but we need to be careful about how some of the chemistry is playing a role when you transition into these nanoparticles. So another information that we can find in the literature is the band gap measurement. So doing some Raman spectrum, this is Miller in 2013 reported something about the length, the pH. They have how many sp2 conjugation of the pH bond on the system. So we still can get some indirect information, but that can help our development of the code. And so, again, they look at the extinction and they say that maybe there are pH with aromatic islands connected by aliphatic bonds. Okay, and so that's something that could be used for snaps too. Okay. In addition, there are several other experimental studies that have been examined. The composition of the nanoparticle, either with the laser technique, I think has been the strongest one for this region. But there are still a lot of uncertainty about the chemistry and why we form these incipient particles. So how do they look like? The current view that I just presented is that there are two main pathways that they can be physical aggregation, and I show you the pyrene dimerization, for example, or how, for example, for the same temperature, the addition of a chain can change the result. And then there is a chemistry going on also. So you can either form a bond, or you can just form a dimer because they have van der Waals interaction, they attract to each other. And so both are valid, and depending on the flame environment, one of the two will have more importance than the others. So if you think a little bit broadly, if you are in a flame and you are at a high temperature and you have a lot of radicals around, chemistry is really important. Things happen very, very fast. You are growing materials. But in other cases in which the temperature is lower, and you don't have enough radicals, and that can happen, for example, in a counterflow diffusion flame, for example, then dimerization is very important. It's the driving force for the nucleation of soot. What the van der Waals interaction, I think that was a question I got before, the van der Waals interaction are not, of course, as strong as could be a bond, but they provide a nuclei for the further growth. So dimers like to stay together, somehow, especially the one with the chains. And that means they will dance around, they will stay together for, let's say, time enough for something else to come in and add and keep the reaction going. So those are two different views that I think we need to consider when we want to think about more deeply about these transition regimes. So I have a series of open questions that I want to share with you. Again, try to provide some information for the next, for the research that you might be interested in. So my open questions are, so if you look at the aliphatic chains that I just showed you before, that basically, for the first time, we can understand this process because we use molecular dynamic simulation. We really look at how the system evolves. And so the question is, a aliphatic chain, do they play a role? Exactly. They are more like outside chain, or they are bridges between? Because you remember, some experiment tells you that there are aromatic islands with aliphatic bond. Now, are those in between, outside? So that's a good question. Side chain could help during coagulation. So maybe the chain will wrap around. And so the 2D pH becomes a 3D with the chain. Does the molecular growth control the inception, or we need the cluster for inception? Okay, so it's just the chemistry going on, or there are conditions in which you need first the dimer, and then you keep adding the chemistry on. There is definitely a need for the gas phase and the pH mechanism to be defined at this point. And also, the more experiment that we can get for temperature and pH, that will be really interesting to all the modeling community. So what are the mechanisms for nucleation and growth? I think those are all questions that we don't have an answer yet for the system. And how the condition in a flame, for example, affect those processes. There are models on soot. They are comprehensive models. What we want is a more fundamental understanding of the process so that we can eventually become more predictive. So not only what we know, but also what we don't know. So if the model is applied to a system that has never seen before, we can get a reasonable answer to that. And also, what are the mechanisms of growth oxidation of soot? So those are all interesting things that there is a lot of research going on this system. So for the particles and from combustion, nanoparticles, I think I gave you some guidelines. I told you that it's a very complex process, that they are coupled. Some of these happen at the same time. So you have first a gas phase. You need to be able to predict this pH formation, and eventually they transition somehow to nuclei of particles. It's not a straightforward process. There are, I would say, two different main pathways at this point, a chemistry, and there is some physics going on. And they are intertwined sometimes. So depending on the condition, you will have one or the others. Once you form those nanoparticles, they will start to coagulate, and then you grow into bigger clusters. Now, just to emphasize a little bit this topic more, and I want to go a little bit beyond this carbonaceous material, I decided to add here a slide about still flame, but materials. So having a tool like a molecular dynamic simulation, I think it can help answer a lot of other questions that are not related directly to soot, but they are related, for example, to material or synthesis of materials in a flame. So one of the projects that we had, and I want to report very quickly a couple of the results we got with MD, was about alumina. So there was an experiment in which they, a group from material science, had this liquid feed flame spray pyrolysis. the turbulent flows, it was something very complicated, and say, and they doped the flame with some precursors for alumina, and then they look somehow at the formation of those alumina nanoparticles inside. Of course, different phases. Okay, and so they had the alpha phase, the delta phase. Those are very interesting for energy application to them. But the question for us was, if I take my, for example, nanoparticles, how the environment is going to drive the phase that I find. So if I want an alpha, what condition do I need to be in? Okay, so this is a different angle, but still related to the combustion and nanoparticle formation for the system. So what we did, and I want to show you just one of the examples with the molecular dynamics simulation. The question was, if I have my nanoparticles in a high temperature in a flame, and I have an alpha phase, and say in a delta phase, there were two different arrangement of the alumina in Al2O3, that's for you. And so the question is, in a flame, high temperature, what do I get at the end? So this is like a more the sintering phase transformation. And so what we did was a molecular dynamics simulation of the system. I want to show you a quick movie, hopefully that will work. And what we understood was, first of all, doing this type of simulation, we could understand the behavior of those ions, diffusivity, something that you cannot just sample easily experimentally, and what happened to this sintering process once you have this different diffusivity. So and I think, yeah, so the first thing I want to show you is this. This is, so this is, experimentally, what they did is they measured XRD, so experimentally of this system. And so what you see is there's green lines here, okay? So they give you information about the structures that you form in a flame. What we did is we ran molecular simulation of those nanoparticles that you can see here. Of course, we don't know the size, but we changed the size between 2, 3, and 4 nanometers of those clusters of alumina, very, very complex things. And then we look at the behavior of two of them getting together. And so what we are able to do with molecular dynamic simulation is to really follow how the atoms and the ion were moving. And those are the results that we got from molecular dynamic simulations in terms of the size. So what you see is basically that the red and the blue, so the size of the nanoparticle between 3 and 4 nanometers were the structures that you could see experimentally here. So see the peak, they correspond to the green peaks that we have here. So at that point, we were able to run, so it comes after, I don't know why, molecular simulations. Does it work? So I want to show you one this, if it works. Okay, how do I get to this? One second. Okay, I see this. Oh, starting. Okay, so this is, again, just to show you the interest or the power of molecular dynamic simulation, not only for the combustion, the soot that we're talking about, but just formation of nanomaterials in flame. So what I'm showing you here is that two different nanoparticles, you cannot see very well, but they had a different configuration. There was an alpha and a delta, and that means two different arrangement of the atoms on the system. We ran the molecular dynamic simulation. That was not easy because you're changing phase, so they are not solid, they are in between, before that. And so what you get is an understanding of the blob that is formed at the end, and then you can compare it with experimental data. So the initial simulation came from experimental data. I can show you this, sorry, here. We found out that the initial particle needed to be between 3 and 4 nanometers because they will agree with the data that we have in the experimental data. Then we ran our simulations here, and they say, oh, great, if they get together, we will form a blob that looks like that, the one at the end. And then we ran some characterization of this blob. And what we were able to understand at the end is that there was a very interesting diffusion of oxygen ions on the surface of the nanoparticle. And somehow, if we computed that with the molecular dynamic simulation here, we came up with a very similar spectrum to the XRD that was predicted in the flame at different sectors. So the bottom line is that using molecular dynamic simulations, we can study phenomena that otherwise experimentally you will not be able to track. So you have a more macroscopic evidence that is an XRD spectrum that gives information about the structures. But if you want to know what is driving this formation, what are the mechanisms, then you need this type of atomistic simulations. Result an overview. And this is, for the first time, we reported the role of the diffusivity for this system. So once you have, an alpha and a delta core, there is this transition of ions. And here I'm just showing you how the size of the nanoparticle affect this diffusion and other properties you might be interested in when you do this. Okay. So let me go back. What is here? I want to, at this time, I'm running out of voices, so I notice. I want to give you a little bit of the preview of what I want to be talking tomorrow, and also put some perspective about what I presented here. So combustion is very interesting. There is a lot of phenomena, and you can approach with different tools if you want. We are very much interested in this atomistic simulation, trying to find a way to answer a molecular mechanism, why this is happening and why, and always bridging with more macroscopic evidence. One of the reasons why I was interested very much in the nanoparticle formation was because of the health effect. And so in order to study the health effect, I needed to know what kind of material is formed from a combustion. And so that's the reason why we do something like a SNAPS and not just a mathematical or phenomenological approach. So I need information about the size, and information about the mass, the chemical composition, and other property, because they all play a role once you interact with the biological system. So here I'm showing you a light micrograph of a section of a human lung that the black dots are all particulate, basically. And so there was a particulate-induced pneumonitis in this lung. And so the message is that somehow we deal with nanoparticle, carbonaceous nanoparticle, and the body is not able to get rid of them. So they can get accumulated in our body, especially the smallest ones, not the biggest one. So we wanted to talk about a little bit about the risk assessment of the environmental nanoparticles as a future. And so when people have done a lot, when they talk about risk or health effect of nanomaterials, they always talk about, there are two components to that. There is an hazard, but there is also an exposure of the nanoparticles. And so many times when people describe this process, they talk about the hazard. So if I have this nanoparticle, nanomaterial, what kind of damage can do to the body? They do a lot of epidemiological study, people exposed to particulate, they induce asthma, they induce fibrosis. But one of the things then when you want to develop a model for that is that you really need to take into account the part that is the exposure. So too often the exposure is always neglected. So if you look at computational work in this field, they've been done on nanotubes, for example. And so the nanotubes with the biological system, that's great. There's a lot, can get a lot of insight. But the question is, what is the exposure level of your carbon nanotubes every day? And I would say that is negligible. Unless you work with nanotubes every day, you don't get exposed to nanotubes. So what you get really exposed to is emissions, for example, from a combustion source. What we were interested in was exactly to combine what I just showed you for SNAPS, so the ability to think about nanomaterials in terms of those specific property of chemical composition and physics also, and see how they interact with the biological system. And so we are doing this. We did this for particle from combustion and also from some engineered nanomaterials. So the idea for tomorrow a little bit is to show you some results that we got. This is just a cartoon of what happened when you breathe nanoparticles. So the nanoparticles somehow, there are a lot of experiments that they found that not only you breathe them in, but they translocate. So you get into the lung, and eventually you find in other organs of your body. So somehow they move through. And so can we use some molecular dynamic simulation or some of approach to study this? So what I was interested is that if this is a cell of your body, mammalian cell, all cells are different, but there is one common, there are three main components, but one where we are interested is the membrane. So if to see the interaction, the nanoparticle from outside will cross the membrane to react with the cell. And so what we did was, can we study how nanoparticles interact with this little area here? And so this little area from atomistic simulation looks like this. Is a lot of nitrogen, phosphor, carbon, hydrogen. So this is called the lipid bilayer. Okay? So if my interest is, my membrane will look like that. And so molecular dynamic simulations of this system will look like this. So we have done some work in which we take a nanomaterial formed, for example, from combustion with the snaps and eventually, and we can look at the interaction, their tendency to cross membrane of the cell. So the question, for example, is, what characteristic of the nanoparticles we want? What characteristic of the nanoparticle create damage to the membrane? And all in the other part is that if you want to design a nanoparticle that will go to the membrane quickly, what is that you need to do that? So as I showed you before for combustion, the type of simulation is a molecular dynamic simulation, and we are very much interested in free energy again. So let me show you, this is an example that I want to maybe go over tomorrow a little more. So this is the lipid bilayer, this is the membrane of the cell. So this is outside the cell, this is inside the cell. So if I take a fullerene, combustion carbonaceous material, and is outside the cell, eventually if I place it in vicinity of the membrane, it will jump in. The free energy tells me that is a spontaneous process. And once it gets close, it will automatically go inside without a barrier. So the number here, the free energy is always below 0. So that's kind of concern for this system. And so we also work with experimental people on this, and then I'll show you some results tomorrow. But this is basically for the C60 that I just showed you, so a carbonaceous nanomaterial. This is a type of experiment that we've been working together with the people. And so what they see, they took mammalian cell, they took C60, and they dumped C60 into the cell. And what they saw after a while, this is TM, the presence of this nanomaterial inside the cell. So somehow they go through the membrane and they cause some damage to the cell. They were present in all the parts of the cell, even close to the nucleus of the cell. So what we do is to extend this molecular dynamic simulation combined with the combustion nanoparticle and see how they affect. So one other thing I want to show you tomorrow is this kind of simulations in which this is again the membrane of the cell. This is outside, this is inside. And so can we use molecular dynamic simulation to look at if I have my pHs, if I have my aromatic compounds, how it goes through, why it goes through, and what kind of a property of these molecules are interesting for this kind of translocation. So just to summarize at this point is that our interest is to understand nanoparticles formed from combustion and also their health effect, so extended to that to biological system. What are the chemistry and the physics or the property of this material that are really driving those kind of interaction? And then on a longer time scale to do what I call reverse design, that is more like given your outcome, so you want a nanoparticle not to go through, for example, or you want a nanoparticle to go through very fast, if you think about drug delivery, for example. What characteristic do you need to have on the nanoparticle for that to happen? So again, we look back at the molecular dynamic simulation and we try to approach this problem from this angle. So at this point, maybe I was going to stop here, see if you have any questions, but what I'm planning to do tomorrow is to extend what I just presented today to give you more details about my molecular dynamic simulation and see how the combustion can be linked to the biological system and what kind of information we can gain with this molecular dynamic simulations. So I think I'm going to stop here, and I'll take any questions if you have.
Yeah, question. So, thank you for your very amazing talk. So I have a question about I'm very interested in the inception of soot particles. So as people who do experiments, so I want to know what kind of experiment is the modeling guys want, and what kind of the experiment data.
So as I was mentioning, I think one of the most important things is the chemical composition. If there is a way to compute, over time, how things evolve in terms of, hydrogen-carbon ratio, for example, or oxygen content of this species, that will be really important for us, for example. So we're trying this different pathway of atomistic simulations that, to describe this as this inception. But experimental data that can corroborate or validate or guide our development will be really critical at this point. So any experiment for chemical composition, awesome, will be awesome.
Okay, another question. So if
as a main features. If you have to ask me the first, that will be the first one I would like.
Okay, and another question is that if the assumption that the inception is by the big pH and linked by the chemical bond, so whether we can think that one nanoparticle is just one molecule.
So the question is, can we think about the nanoparticle is one molecule?
Yeah, it's the initial nanoparticles can think about just like one molecule.
So what I was trying to show you is that, first of all, yes, the big pH can form a dimer. This is a circumcoronary that is huge, but the concentration in the flame is very, very low. So from a statistical point of view, yes, you have the tendency to grow, but you don't have enough of those. So what likelihood is happening is that you have a combination of the two approaches to grow in size. So if your nucleating particle is, let's say, 200 carbon, it's unlikely that it is one molecule, basically. But it's mainly the dimers and the chemistry at the same time that they are playing a role on those things.
Yeah, I understand.
Yeah.
Thank you.
Showing the growth of the molecule on the edges is fascinating. Have you thought about the oxidation piece? Would oxygen sort of nibble at the edges, or would it interact differently with the particles you're showing?
We are starting working on this. So one of the problems, this is a great question, it's very important for us, is the rates, again. So somehow SNAPs, I love SNAPs, but SNAPs needs information about the rates of the class of reactions. And so we can find something in the literature that is an approximation, but we're trying to come up, I would love some quantum chemistry for this type of reactions. Yeah, so the oxygen, especially from the edges, and then it can remove, for example, you can have oxygen coming in and removing like CO, like from a ring. From a 6-member rings, if you have oxygen in, you can have CO formation, and then maybe you have a 5-member rings that you form. So the chemistry can completely be affected by this. So it's great, very interesting.
Okay, thank you.
Hello.
Hello.
Have you thought about nanoparticles formed in the atmosphere, such as aerosols, formed from, say, volatile organic compounds oxidation? Because I think your methodology could be very interesting there as well.
Yeah, that's a good point, Mani. So I have not done anything, but in principle, you can take some nanoparticles that are formed from combustion and look at molecular dynamics and oxygen coming in, all the chemistry. That happens. The temperature is different, so the things are going to be different, but I think there is definitely an avenue to use that. So that's very interesting for the future. I think that's once you have this material that is formed, the two avenues is more the environmental effect, that's what you're talking about, and also the biological effect on the human health. So far, I've been pushed more on the human health effect, but definitely that's a very interesting area.
And from many experiments done here at KAUST, I've realized pressure is very important towards soot formation. So how does pressure fit into all this picture? And do you have any insights on that?
Yeah, so definitely there is well, there are different stages in what I pictured here. This is working basically high pressure. So in the approximation from 1 atmosphere on, SNAPS works, basically. For the gas phase, of course, we have some dependency that we get for our precursors that are pressure dependent. So we take into account that with the gas phase chemistry. Then we get the precursor that can be fed into SNAPS. So that is, at the moment, the influence of the pressure in our system. But SNAPS is working from 1 atmosphere on.
Well, just a comment by me on your bullet number 2 says, what's the interactions with biological systems? If you think, it comes as a surprise to me when somebody explains to you, but I had several friends who started in particle size instrumentation, and they formed companies to sell instruments to measure particle size. Most recently, they're employed in smoking machines that have these new electronic cigarettes.
Yeah.
And the argument being that the delivery of chemicals to your body, that particles are usually what's carrying the active ingredient.
Yes.
So there's a tremendous amount of research going on. What is going on with these electronic cigarettes?
Yeah.
Do you have any comment on that?
So that's all open question. But so what I show you is that the nanoparticles that basically, for my case, was going through the membrane, right? But sometimes that could be also scaffold. So basically, it's delivering one of the compounds. They get to the membrane, and only part of the functional group that is attached to the external part can go through. So those are still open question, but not necessarily I see the nanoparticle just per se going through, but it's also as used as a delivery scaffold for those additional compounds. That's a great point. So there is a lot that we need to understand.
So a comment to the region here. When I go back to California, I rarely see anybody smoking cigarettes. Likely they'll be banned. Nearly everybody I know that still uses nicotine is buying it in an electronic cigarette. And the American Medical Association encourages that. They discourage that you use nicotine, but if you're going to do that, they said, do not use cigarettes. Instead, use these vaporization devices. So the times they are changing, okay? Any other questions?
Yeah.
You're allowed to comment, as did I.
Comment on your comment.
Okay, comment on my
There is a recent study that correlated the e-cigarettes with higher cancer rates. So that might go away with the cigarettes as well.
There will be numerous such studies, no doubt. Okay.
So you can think that, you know, if it's more difficult for a big chunk of nanoparticle to go through rather than a piece of carcinogenic material. So if you have a small molecule, I don't know, pyrene or benzopyrene that is highly carcinogenic, let's say attached with an aliphatic bond to this cluster of nanoparticles, it can just get to the membrane and then only the carcinogenic part, for example, the small piece will go in. And it's definitely easier than go through all the nanoparticles. So I guess that speaks to your point as well. Carcinogenic molecules can be easier for them to go through.
Okay, we continue tomorrow at 9?
Yes. So thank you very much, Professor Violi. Today, we'll have a gala dinner. Everybody's invited. That will happen around 6 o'clock, so there'll be a bus for the students at Combustion leaving at 5:45. And I think many people have cars as well, so feel free to drive there yourself.
It's a nice walk.
Or you can walk also. It's about less than 20 minutes, 15 minutes or so.
15.
So yeah, dinner will be served around 6:15. We look forward to seeing you there. Tomorrow we start at 9.